Okay, good morning.
Good morning.
Thank you for coming.
Thank you.
I want to thanks a lot Professor Aidas from MIT Melbourne University for accepting our invitation to do this interesting lectures. I guess I am sure that will be very interesting for our PhD students and all the interested persons that are connected this morning. In Australia is at the moment 6 o'clock, 6:30, if I am not wrong. And
5:30.
Okay. And I just want to spend a few words to introduce Professor Aidas, who is full professor of applied mechanics and leads the simulation of advanced materials and structures research group. And he has 20 years experience in design, analysis, optimization, engineering, materials and structures with specific focus on computational mechanics. And this is why I think your lecture, his lecturers will be of interest for all of you. And he get his PhD at Monash University in Australia in applied mechanics, and has previously worked at the University of Auckland, New Zealand. And I went to New Zealand when he organized an international conference computational for everything, computational aspects of science. And he is currently the president of the International Congress of Mechanical Behavior of Materials and director of the executive committee of the International Congress of Fracture and many other in charge. And Professor Aidas has been granted several national and international awards. And we do appreciate his presence in our PhD course, and we are very glad to host him, and of course honored to can listen his lecture. And please start your lessons.
Thank you. Thank you very much, Professor Patricia Trovalusci and your team for your kind invitation to Italy virtually. So I'm thinking I'm now in Rome, so I will try to behave like a Roman now, okay? I should have put a virtual background of Rome, which I will do tomorrow. So today, thank you very much. And today I am very pleased to bring to you all the doctoral students, our research from RMIT University, where I belong to School of Engineering, particularly aerospace engineering and aviation. So I'll be talking about two aspects, basically multiscale failure modeling of sustainable multifunctional biocomposite and cellular materials. So before I start, so I want to give you an overview of what the nature of my talk will be. Now, what I'll be mainly focusing on, starting with the practical application of multiscale computational modeling for design and analysis of advanced materials. So, and all of these, of course, have got a quite detailed mathematical background, mathematical derivation and concepts. So, and if I want to present the whole mathematics of it, I have to give a course of 10 days. So because I only have 2 hours today and tomorrow, 2 hours, so 2 lectures, I would give the overview, but mainly I will try to give you the relationship of computational modeling, multiscale modeling with the design and application for real aerospace. So I want to bring that picture to you as a doctoral students, because often we do PhD and we do not recognize the importance of the theoretical work, the numerical modeling we are doing for practical design analysis. So this is what I would like to bring through my talk. But however, if any of you are interested in more computational aspects or more theoretical aspect to know more the mathematical background, please do contact me, and I will send you my papers, and I can discuss with you, I can explain you more things. So I'd like to share my screen now, which will be shared to you in a moment. So hopefully you can now all see my screen, I believe. Okay, so if you can see my screen, let's start then. So my talk is Introduction to multiscale failure modeling of structures. Particularly, I'm focusing on sustainable multifunctional biocomposite and cellular materials. There are two things here. When we talk about biocomposite, we mean composites which are made from sustainable materials, so which are recyclable and which are renewable. That means, which is very important for the next generation materials industry, because the world is now moving towards sustainability, renewability, and eco-friendliness because of the environmental concerns. And secondly, I'll talk about cellular materials, which represents lightweight materials. So the materials which can be used for weight reduction, particularly in the context of aerospace, but also you could use them for automotive, civil structures in many places where we really need to reduce the material weight by replacing the previous generation of materials with the next generation of materials. And I will show you how multiscale modeling and analysis could be used for these design purposes. So for that, I'm currently, as Professor said, group leader for simulation of advanced materials and structures group. We call it SAMS, which is within the Center of Multifunctional Materials in RMIT University in Melbourne. So I would like to acknowledge first a number of my students who have contributed to the work, and also my collaborators from RMIT University and University of Auckland, both places. So I'm very glad to discuss about those. To start with, the ultimate goal for my talk is to design new materials and structures which can resist failure. So it could be designing cellular materials or auxetic materials or functionally integrated materials which can replace some of the conventional metallic materials in aircraft structures. So one part is advanced materials. The second part would be what we call the response of materials under loads, which means the failure and fracture of materials, and how we can design better materials to avoid fracture failure or to ensure durable material response. So with that, let me start my talk. I will give you an overview. I will start with an introduction of my department in Australia, because many of you may not be familiar with RMIT University in Melbourne, which is a beautiful city. And let me talk about some brief intro about aerospace engineering and aviation, and also the RMIT Sir Lawrence Wackett Aerospace Research Center. So our mission and vision is, we are a leader in aerospace engineering and aviation research and education in Australia. We got a ranking of ERA 5, which is the highest Australian government ranking, representing the quality of universities. So the ERA rating is given between 1 and 5. 5 is above world standard. So RMIT is denoted as above world standard in aerospace engineering program. So our objective is to foster a world-class student, educators, and research community to develop enabling technologies for next generation air transportation systems. And this has basically two objectives. First, at the airframe, aircraft and airframe level, where we are looking forward to design structures with increased reliability, improved design techniques, intelligent and autonomous solution. On the other hand, we are looking at more system level with enhanced operational capability, green or renewable recycled material, and safety system to deliver aerospace aviation's critical outcome for industry partners. Now, for both of the approaches, we need multiscale modeling technology, but my research is mainly on the aircraft and airframe level, basically structures and materials domain. So basically, our research strength is we want to develop enabling technologies for next generation air transportation systems. And to do so, To be able to do so, we will be looking for potential capability areas down to key technology areas. For example, the first topic of our theme of research within aerospace is aerospace materials and multifunctional composites, about which I'm going to talk today, looking at a number of aspects we focus, for example, through life support of aging airframes and life cycle cost, integrity assessment and airworthiness, damage tolerance and progression of failure, and structural health monitoring, robust design and optimization, and finally, smart materials and structures. So this is our focus of research mainly. But in addition, we have another group which deals with unmanned aircraft systems and design field operation, where we are mostly looking at architecture system design, trusted autonomy, flight operations, new generation from bio-inspired and MAV, high altitude, long endurance, unmanned aerial systems, US integration, sense and avoid, and safety regulations. Finally, we have got aerodynamic loading and multidisciplinary design optimization group, where we are looking at fluid structure interaction, aeroviscoelasticity, aerocyberelasticity, vibration suppression, and advanced solution for different air platforms for better control, and also system identification, energy harvesting, hypersonics. Finally, we have an aviation sector where we are looking at avionics, air traffic management, and mission systems. For example, future ATM. Now, ATM is not the bank ATM, it's air traffic management. Key technology enablers, mission system for civil and military aircraft, human factor-based solutions, and different sensor systems. So all of these need significant data fusion, data analysis, high level of multi-scale modeling technology coupled with design and innovation. So this is what we would be extensively using in our discipline, the simulation and modeling technology for all of this. But of course, my focus would be aerospace materials and structures area. To give you a bit of name, why our center is named at Sir Lawrence Wackett Aerospace Research Center, that's historical. Sir Lawrence Wackett was a famous aerospace personality within Australia. He was one of the first pilots who built a glider long before, during the Wright brothers' time. So we honored Sir Lockett Lawrence and gave the center Sir Lawrence Wackett Aerospace Research Center. In terms of our areas, as I said, aerospace materials, structures, avionics, design and manufacturing process, and power and energy propulsion systems, and finally, dynamic aerospace system. So I think this overview is important. I'm not going in further details, but I can discuss any of these. And this gives a different perspective to your department. I know you are Department of Civil Structures and Geotechnical, but I can show you the technology, modeling technology we are using in our aerospace and mechanical context can be applied to structures and geotechnical as well, because the fundamental science and physics are common. Now, we work with a lot of industries here at high impact translational research, particularly DST group, which our defense research arm of Australia. And the DST stands for Defense Research and Technology Group, which is the defense research arm, Australian Defense Force. We work with a number of divisions. Then we work with Boeing, Ford, Materials Center, Defense Tech, which is a company local, US Office of Naval Research, Thales, with ATM area, and also many companies which are local SMEs for US technologies, and of course, Defense CRC. So you could see we work with industry quite significantly, and as a result, my presentation, my lecture will include some of the perspective of modeling and simulation in the industrial concept, but I will go in details as well. In this sense, let me summarize my research group, SAM's group. The key focus is modeling methods and novel structures and materials. So coupled solver algorithms, particularly our lot of modeling methodology is based on mesh-free and finite element method technology. And also based on mesh-free and finite element method, we develop significant number of coupled solver, both one-way coupling and two-way coupling. So in both ways, and these are based on a multi-scale modeling approach. With that, we couple with novel materials and structures. That is our focus, looking at detailed constitutive laws, microstructure effect, and damage mechanics. So, and our applications are mainly three themes: structured multifunctional materials, dynamic fracture and impact, and damage tolerance design optimization. So mainly focusing on fracture and failure of materials. So first theme, structured multifunctional materials, we are looking at architected material design. That is where the multiscale modeling really comes into play. We are embedding microstructures at different scales, from real microstructure level to larger scale. So we are embedding a lattice structure within another lattice to create multiple scale to tune the property of the macro material. So this is really important area of research, what we call architectural materials. And then we are looking at auxetic materials, which are materials with negative Poisson's ratio. So if you apply a longitudinal strain, you do not get a negative lateral strain, you will get a positive lateral strain. And we are looking at different design and architecture, multi-scale design of auxetic materials for doing that. And then these are auxetic materials is mainly used for statics. Now then we are looking at dynamic materials or dynamic behavior of materials, in which we are looking at metamaterials and then functionally graded materials. That's all about structured multifunctional materials domain. Then moving into dynamic fracture and impact, which is a very key focus of our work, particularly with defense, designing land vehicles against blast and impact, mine explosion. So we are designing a lot of materials against ballistic impact, land mines, explosions, bomb threat, etc. And that is we are looking at impact fracture and designing composite and ceramics for impact proof or impact resistant material shells, and doing a lot of brittle and ductile damage models to analyze the impact response of such materials. And finally, working with aerospace industry, particularly in aerospace, one key focus is damage tolerance design optimization. So you cannot avoid damage in a structure, but the focus of our research is in the presence of damage or defects in a structure, how can we predict the life of the structure, how long the structure will operate. So that is something damage tolerance design optimization we are working on in that as well. Finally, what is the application of these three themes? Our final applications are these three: multifunctional lightweight structures, morphing structures for aircraft, and damage tolerance structures. Damage tolerance structures is from aerospace and transport, like automotive industry, or transport like buses, train, trucks, where we are replacing metals with composites and designing lightweight composites. Morphing structures is really a fantastic area for those who are interested in aerospace, but we can use morphing structures in buildings as well. So it has got applications in the civil domain. But our application, of course, we are designing smart wings with novel materials, optimizing the wing shape, material distribution, using lightweight lattice materials to achieve weight reduction and to obtain enhanced performance from these smart wings for high-speed, really supersonic military aircraft, as well as mainly military aircraft. And if you know, the F-35, which is the next generation US fighter aircraft, which was built in partnership with US. So Australia is a partner in developing that. And we have done some work on the design of F-35 in collaboration with the DST, Defense Science and Technology Group. And finally, for many applications, of course, multifunctional lightweight structures would be a key, where we are looking at strengthening and failure mechanisms of those and multifunctional properties. For example, how can we impart fire retardant property to a structure so that if it is subjected to fire, it will not cause a catastrophic failure. So that's a summary, and we do work with a lot of applications: aerospace, automotive, defense, biomedical, marine, sports, etc. So before I go into the multi-scale modeling technology, I think it is important I give you a perspective of what is our main solution system or solver system methodology we use. We use basically two methodology. One is a mesh-free method, a smooth particle hydrodynamics, and another methodology is finite element method. Now, the finite element is very standard conventional method. We all know this, so there is no point for me to highlight that. But the mesh-free method, I think those of you who are doing PhD here and you are working in computational modeling, some of you find this interesting, and I'm very happy to provide you more information or work with you if you're interested to work with us in this mesh-free method, which is very interesting, and I will tell you some background of it, some mathematical background. But why we are using mesh-free method or SPH, which is called smooth particle hydrodynamics, these are the reasons. The benefit of SPH is you can easily do coupling between multiple physical processes. For example, elastic plastic solid deformation, heat transfer, microstructure transformation, phase transformation. Even you can interact a fluid flow within a porous medium, and the stresses and strain developed due to the fluid flow within a porous medium you can analyze. Okay, so that's the benefit of SPH. Second thing is, it's an inherently nonlinear transient analysis method. For example, particularly if we use nonlinear finite element method, which can be problematic, which can be computationally very expensive and may pose stability problems. On the other hand, the SPH method automatically takes into account the geometric and material nonlinearities of the problem. But secondly, when you talk about the constitutive behavior, say you are implementing crystal plasticity for microstructure transformation, or say you are using dislocation dynamics for plasticity for metal. For example, if you are using composite materials, you are implementing micro damage model. So, or interface damage or fiber matrix interface. Now, all of these or many of these depend on things like dynamic response. For example, strain rate is often a factor which controls the constitutive response of some of the composite materials, particularly matrix could be viscoelastic or viscoplastic. So to implement this rate dependent model, it is often useful to use an SPH analysis framework because it automatically takes into account geometric nonlinearities, and it can track the evolution of history-dependent material properties like cumulative plastic strain damage, gas, microstructure, etc. And the reason it does that is because SPH is a Lagrangian method, right? So a piece of material which is representing a blob of material. So one SPH particle will represent a small piece of material, okay, within the body. And as you deform, if you are fracturing, which is discontinuous deformation, this small piece of material will move in response to the stress field in the body, in response to the load. And it can store all the state variables. For example, microstructure, damage value, all the properties. If you have metal, plastic strain, or fracture mechanics parameters, all of them could be stored with time, and that could be used to implement effective advanced constitutive models within the system. Finally, the solution control or the accuracy control is same, the convergence issue is same. It is very much like FEA. So you can do similar things like stability analysis, patch testing to derive the accuracy bound of this SPH formulation. You can use H adaptivity like we use in FEM. Finally, because SPH, which I will show a bit more details, since SPH creates a higher connectivity than FEM, the solutions, SPH solutions tend to be more stable under high deformation for large deformation problem or high strain problems, okay? And stress continuity across the analysis domain is ensured. We know in FEM, if you use the standard FEM, the stresses are not continuous across the boundary. right? So across the boundary, the stress will not be continuous, but with SPH, we can enforce a stress continuity across the boundary of the system. That's the benefit of using SPH. Finally, now let us look at what this SPH method is really. Now, as I said, it is a meshless approach, meshless method. It was developed to model astrophysical systems. So it represents solid and fluid as a series of interacting pseudoparticles. So instead of discretizing a structure with mesh, we discretize a structure with a series of particles, and the properties of fluid or solid are stored at each interpolation point. So the center of the particles act as an interpolation point mathematically, and we use a weighted method, a weighted sum of neighboring particle properties to calculate or to interpolate any state variable or any property at any point. And same way we can use, because we are using the particles, as one particle will represent a piece of material or blob of material. We are using a number of particles. So mathematically, the center point of the particle acts as our interpolation domain. And we know the properties like, say, displacement, stresses, strain, damage, microstructure, anything we need, we can store at the particle center, and we can then construct a continuous field variable by using a Gaussian type functional interpolation form. And you can use that interpolation function and differentiate it, take the derivative of it to calculate special derivatives where we do not need the presence of a grid. So let's go a bit of maths behind it. So you can start with this identity for any function can be represented by the integral of that functional value at that point multiplied by a Dirac delta function, and you integrate. Now in SPH, what we do, we replace this equal to sign with an approximate. So we approximate the function at any position vector r, and we represent the Dirac delta function by a wet function w, which is basically similar to a radial basis function, and a controlling parameter, a spatial distribution parameter, which is h, which plays the same role like mesh size in finite element. And what we do, mb is the mass of the particle b, and rho b is the density. Ab is the value of any state variable, displacement, pressure, stress, strain, plastic strain. Even if you are fluid, we can be velocity, can be displacement. So any variable of interest we are trying to use as a primary variable, we can use A for. And then you can sum about all the neighboring particles, b equal to 1 to n, to calculate the value of any function at any arbitrary point within the domain of analysis. So this is how you construct a continuous field variable representation by discretizing a structure or a body or an object with a set of particles. Now, this is an approximation. And now what we do, the element volume, dr, is replaced by this. And this is a known analytical function which approximates the delta function. Now, if you differentiate, if you take the gradient on both sides, we can get the gradient of any function by getting the gradient of the wet function. So you can differentiate both sides. This part is constant. So this part is a function of r. So if you are taking gradient with respect to r, the spatial position vector, you can differentiate with respect to r on both sides, and you can thus see we do not need a grid, a mesh, or a cells to calculate derivatives. In FE, we would need to use the grids, and we would need Jacobian matrix to calculate the derivatives. That is what our FE accuracy is affected by the mesh resolution and mesh quality. But here, we can differentiate this straight away, and we do not need any gradient to calculate the derivative of functions. And to give you an example, these are some of the fluid mechanics equations, because fluid mechanics SPH was first applied. So I've just picked some fluid mechanics equations. This is continuity momentum equation of state and nodes. So you could see this is the momentum equation, Navier-Stokes equation. This is the left-hand side, which is the total derivative of the velocity. So this is the acceleration term. This is the pressure term. This is the liquid boundary viscous term. This is the gravity, and this is the boundary force. This is to implement the boundary condition in the problem, okay, to stop the particles penetrating the boundary. And you obviously need an equation of state and kinematic equation, which is velocity derivative of the position vector is the velocity. But I think most of you would be interested, elastic solids or solid mechanics. You can do the same thing. You can have a continuity equation. So my left-hand side is an example of a number of partial differential equations we solve. On the right-hand side, we wrote those PDEs in SPH approximation. For example, the left-hand side, we have a continuity equation in solid mechanics, whether this is an SPH approximation, you replace the gradient with the gradient of that wet function, and you use the difference in velocity between particle A and the neighboring particle B, which you sum about B to get the interpolated gradient or derivative of density at any point. So this is time derivative, of course. You can get it that way. Momentum equation, this is the momentum equation for simple elasticity problem. For dynamic analysis, for transient analysis, you can replace this equation with, again, you can calculate the acceleration or dvdt at any point by summing over all the surrounding points. B goes from 1 to n about this stress tensor, and this is a stability term. We call it artificial viscosity. And then we dot product it with the gradient of the wet function, and we add any body force, such as gravity, as to be in the equation. Then we can use stress relations like the deviatoric stress and the total stress and the pressure to get a deviatoric stress equation like this, and then we can discretize in SPH form. Similarly, we can calculate the strain rate in real form, and we can approximate the strain rate using SPH equation. You could see these are the gradient of the wet function with respect to the directional derivative, and these are the velocity difference. So by using the velocity difference and gradient of the wet function, we are able to calculate the strain rate on at any point within the domain. In this case, because SPH we often use for large deformation problem, so we use what we call a Jaumann rotation tensor. So we use a rotation tensor, which we again approximate. So this is depends on the velocity gradient, and we approximate that using again SPH approximation, and we use the rotation tensor in this stress evolution equation, so that we can model the large material rotation and large deformation of material. So large strain formulation is what we really use, along with in all our multi-scale based model. We need equation of state. We use sometimes the pressure density relation and bulk modulus sound speed relationship as well. So some quick example. This is modeled with SPH. These rubber rings were modeled with hyperelastic materials, and you can see the stress wave propagation through the material. So we can very easily naturally model the contact mechanics, large deformation, hyperelastic constitutive models within an SPH formulation, and we can see the stress waves. An example of a multiphysics. So this problem, you have a piece of liquid, a bucket of liquid. So the white thing is the wall, and this is cooling. And when the liquid is cooling, you have got heat transfer, but heat transfer is coupled with the solid mechanics into it, the metal solidification. So you could see as the liquid cools, so this is the temperature distribution. So the hot liquid is in the middle, cold liquid is at the boundary, and you can see the depression or the dropping of the top surface due to the shrinkage. So in this case, thermodynamics, thermal stresses was coupled with the shrinkage, with the phase transformation and solidification, and we can couple it with the microstructure as well. So it's a true multiphysics coupling between different phenomena. And as I said, SPH is very good. It offers a natural framework for multiphysics analysis of systems, which we can demonstrate here. Finally, the most important cases, applications where we are applying the SPH method is a dynamic fracture, so dynamic impact fracture. And when people talk about what do you think about dynamic impact, I say, look, when you get up in the morning, go to your breakfast table, take a tomato, and think you are shooting it with a bullet. How did it look like? What did it behave? It's a viscoelastoplastic material, a tomato. If you happen to get a chance, which you will not do, so don't do that, or you can imagine in dream that you are shooting a tomato with a bullet, you can see the frontal shock waves of material, of viscoplastic material. So the frontal shock wave and what we call the back spatter or the reverse shock waves being produced. But what we are interested in when we design such kind of armors, which are designed to protect us from ballistic projectiles and explosions and blast, how would we design the projectile to be able to prevent such kind of heavy catastrophic impact fracture? So some of the cases we have used SPH, and it has also got multiscale damage model embedded in it, which I will highlight maybe some other time, but I can give you the paper. So this was done to investigate what happens when different shape of debris impacts a plate. So this is like you are designing an aircraft surface where different types of debris is impacting, and they are looking at the energy absorption of these materials. And this can be used for designing, for example, under storms, you may have some small objects impacting a building. And we can use it to analyze and to study the effect of the shape of the debris. So completely circular, square, and annular. You can see the annular one has brittle fracture across it. The circular one gets a straight vertical fracture plane, whereas the square one suffers a diagonal fracture. So we can look at the dynamic fracture response of these different materials using SPH. Then we looked at impact fracture, the effect of constitutive relation. So we have two projectiles impacting a brittle column. One projectile is perfect elastic, the second projectile is elastoplastic with the plasticity parameter determined from experiment. So this is like a Taylor test. So you could see the completely elastic projectile caused significant fragmentation of the column, whereas the elastoplastic projectile suffers a lot of significant plastic deformation at the head, at the front end of the projectile, and which dissipates a lot of the energy, which means you get less fracture, less significant fracture, and in the column. The column is of course made of concrete, and the projectile is made of steel in this case. So a steel projectile hitting a concrete, for example, and in this case that was simulated. What we are effectively realized that the constitutive behavior of the material really significantly affect the dynamic impact fracture of such a high-speed projectile impact, which was the clear story that we needed to assess for defense structures. Then we looked at how do we design the ballistic projectile on a thin target, for example, armor vest or very thin kind of protection materials. How do we design so that we can protect us from potential projectile impact? And this was a work we did looking at a ballistic projectile impacting a thin ceramic plate. Look at the fracture pattern. You can see the debris cloud, the frontal cloud here. Around the fracture zone, you can see the cracks emanate radially, but this crack do not reach. Upon reaching the boundary, you can see the cracks kind of branches into multiple cracks. So why that happens? When this crack near goes to the boundary, because this is a dynamic event, a propagating crack here, look, the crack is propagating. They are met with the stress waves, which are reflected from the free edge. So the stress waves reflected from the free edge and create rarefraction or compression waves. And these compression waves interact with the advancing crack and causes crack retardation. And as a result of that, you could get multiple branching of crack within the material. So this was an example where multiscale model was used to analyze, assess impact fracture of different materials. We then looked at glass, and the important thing is if the glass is small, you can get significant impact fracture because again, It's a brittle material, so the cracks will start from the middle of the domain, the debris domain, or what we call the central fracture region, and it will propagate towards the boundary. And when it is reflected from the boundary, it will interact with the advancing crack. But if the plate is longer, as you will see, in this case, the cracks lose energy before it reaches the boundary. But what we can see, a lot of bending of cracks and branching of cracks. So we have compared some of the what we call projectile holes. So these are holes created by projectile with our simulation for different glass properties. So these are the windshield glasses. For different glass properties and the plastic or polymeric coating they put on the glass, we looked at different glass properties and polymeric coatings and tried to assess the design of the glass, which will minimize the impact of such projectile impact. We can see these are all some of our collected pictures, and this is the simulation. We were able to predict the debris zone and also the crack path, including the branching and bending of the cracks in our simulation. This is the debris zone. This is what we observed from a field data through an experiment, and this is the debris zone we observed through our simulation. So again, we can see very close match. Even quantitatively, if you measure this debris zone and the experimentally observed debris zone, the crack path, the length of the crack, the length of the branches, all of these we find closely similar. So the simulation model, we were able to create reliable simulation model using SP8 and multiscale technology to be able to predict such dynamic fracture. Now, obviously, I can go more details on actual multiscale method, which includes effect of inclusions in the domain, effect of crack damage, which probably if you're interested, I'm very happy to go through, but there are a lot of things of mathematical details, which maybe next lecture, tomorrow I can talk a bit more, maybe 2 days later I can talk a bit more. We then use this for composite because this is a workshop on composite materials. These impact fracture you see on these panels, they are caused by, again, projectile impact, but these are composite, but not pure composite. These are called fiber metal laminate or FML. So you have a metal layer and a fiber reinforced polymer layer kind of alternately placed together, okay? And that creates a panel. And in that panel, you can resist significant out-of-plane deformation because the metal provides quite a large out-of-plane stiffness, and the composite fiber reinforced polymer layer provide the tensile stiffness, but also because their density is low, it helps to make the FML panels lightweight. But we are interested in understanding damage mode in these FML panels, and we found we can use the multiscale method to look at interlaminar damage, the out-of-plane damage, debonding, indentation damage. All of these could be modeled and analyzed using a multiscale method. So these are the back face and the front face. So what is our goal? We want to apply multiscale technology for and to understand for different types of FML, like with Plytron 3x2, 20x3x2, FRTBE. So this is using to explain in more details. So these FMLs are using an elastomer. So you have a metal layer, you have a rubber reinforced with fiber. So what we call elastomeric fiber reinforced elastomer layer with the metal. So we are modeling the fiber reinforced elastomer, which is kind of hyper-elastic composite material. And then we are using metal to model the plasticity. That's why I have to work on both metal and composite in terms of multiscale technology, because often we design hybrid materials. And our goal is we don't want perforation. So we would like to design this layup, choose the material in a way. So for the design ballistic speed and the projectile mass, we have to avoid the perforation. So this is our key goal. And we found 3x2 laminate showed improved resistance to impact perforations, whereas 3x2 FRTP laminate completely stopped the indenter, which is what we really want. So basically, in my overall multiscale mechanics, which I use with when SPH is the base macroscale method, So our macro model is often the SPH model, the continuum body. Within that, I embed what we call RVE, macro RVE, where I solve localized problem using FE. And then suppose we are using FE with this green voxels, we use FE, and each green voxel, because suppose you are using a phone node element, that means each FE element, each finite element has got 4 Gauss points. And then each Gauss point, we are using sometimes nano, sometimes meso. You can call these scales anything you like, depending on the time scale. We have used in micro RV, we call them, this green, we use any method, phase field method, molecular dynamics method, method which is suitable for the scale, the method which is suitable to assess the physics at that scale, to evaluate the quantities of interest at that scale. So this is what we have used in our generic multiscale framework. And these are normally we try to do it both way coupled. So you have a macro model which provides input to micro model, and the micro model provides output to macro model. And we start with macro level analysis, and then input from the macro model will be used. It could be like a deformation gradient. It could be like some plasticity parameters. It could be like a boundary condition, which we apply in micro model. And then finally, we can go for another level, either from micro or meso model. We can either go to micro, or if we are in the micro model, in some cases, we have looked at nanoscale. And I'll give you a quick example for one of our work, where we looked at polymeric functionally graded materials to tailor the properties. And this was a PhD topic of one of my PhD student, Mehdi Amirpur. So multiscale nature of FGM means, so functionally graded materials, if we use, we have a microscale voids, which is you cannot avoid. Suppose you use a method like 3D printing to produce this functionally graded polymer, you cannot avoid microscale void, or sometimes you will get impurities, which is a mesoscale, millimeter scale inclusions. But your component macroscale would look like this. So this is a functionally graded. The gray area is a material of higher density, and the light area is the material of lower density. So although it looks a continuous property distribution in a macro scale, but in a mesoscale, you will have inclusions. In a microscale, you will have voids. So that means if you're looking at the failure mechanics, so you have to take into account micro, meso, macro in this kind of framework. So we have a void model with microscale, which will provide the constitutive parameters, the continuum damage parameter to the mesoscale. And in mesoscale, we will include the effect of these inclusions as a microstructural parameter. And we will take the microscale parameter and mesoscale parameter into our damage formulation for macroscale damage analysis. So the key things we will look at: material compositions and properties vary spatially in either one direction or both direction. We want to avoid stress concentration and discontinuity, and we used multi-material printing. So these are some of the specimens we made, and we first modeled what we call coupled plastic damage in polymeric material. So we created based on plasticity theory, we came up with the plastic damage plastic multiplier. Again, I could explain this for a whole day today with mathematical equation derivation, but I want to first give you an overview of the application and the topics and relation to practical materials, right? If you're interested, I can send you the papers, which has got all the details, all the mathematical details, numerical implementation, all the details. And then we have got a damage multiplier, which we use in the continuum damage model. And then we implement this method, which we start with an elastic predictor. And then we check for the yielding response by comparing the yield surface. And then if it is yes, we do a plastic return mapping. And we then use Newton's method for finding the exact value for lambda for the plastic return mapping, which we then use to update the R, and then the plastic surface stress. And then we use this deviatoric stress formulation and use one of the plastic constitutive law to update the plastic strain. You could use any plasticity law embedded here. We normally use, Wilkinson's model or any plasticity model we use. And if it is no, from here, we go straight here, we check for the damage. So if the yielding doesn't happen, has the damage happened? And we use a damage function here, which we can update, what we call the damage corrector. Using the damage corrector, we update the D variable and we update the stress matrix or stress tensor using the damage variable. And we continue this operation until we satisfy a failure criterion. So we have used this to analyze what we call a control stiffness development. So we want to create these FGM, functionally graded polymeric plates, by 3D printing using multiple materials, so that we have a homogeneous plate which provides a symmetric distribution. This is the deflection. If you apply a uniform load on the plate, this is the deflected or deformed plate profile. Now we looked at, this is the red is our reference, which is a symmetric distribution of an isotropic plate. Now we can control the property variation through the thickness, which is, we can control the property variation through the thickness, like here, my cursor, or through the length. Now either of them will produce a asymmetric deflection pattern or asymmetric stiffness, which out of plane stiffness, which we may be necessary for us to look into. And you can see the green one is variation of material properties along the length, and the blue one is the variation of material property through the thickness. So you can see if you vary along the length, you can shift the symmetry to the left. If you vary the material property through the thickness, you can create the symmetry to the right. So you can control the symmetry or the distribution characteristics of the modulus, which is the macroscale modulus or macroscale stiffness in the out of plane deformation, by varying the gradient in different directions. We can tailor the stiffness, and we can use the multiscale plasticity damage analysis in a coupled way to design these materials, which we did. There are a lot of options, particularly when we talk about additive manufacturing. There are a lot of microstructure defect flaws, which are, the base material may be isotropic, but if you look at a material microstructure due to layer by layer manufacturing, you can see significant anisotropic nature. Vastly different properties from base material with microstructure anisotropy. This will influence damage, defect characteristics, and failure mechanics. So damage tolerance assessment needs to address this, and multiscale model is the solution for these things. So this was my first hour overview, and there's lots of reference we have used. And then I will then move to the two key topics which I proposed in my abstract. First one would be more focused. So I will take two of these. First one is coupled multiscale modeling of understanding failure behavior of sustainable composite, natural fiber composite. And the second one will look at multiscale probabilistic analysis of evaluating micromechanical failure behavior for closed shell forms. So we will apply these multiscale modeling, and there are a lot of other work I have taught, but I have chosen two topics. One would be, how do we model natural fiber composites with multiscale damage? And the second one will be, how do we design or analyze lightweight materials, lightweight cellular materials using multiscale modeling? So this would be two things, and I would probably thank you, my team, who has contributed to these two separate lectures, which I'm going to present. So here I would like to see if there is a chance or you would like to take a break. Please let me know, because I have done 1 hour exactly. And the next hour I will do lecture 1. But I would like to see from your team whether this is the time to take a break or what we do.
You hear me? Se non mi vede? No, la vedo. La vede, perché poi non fa vedere loro, non possiamo autovedere. Rai, could you hear me?
Yes, I can hear you.
Yes. Do you want to stop for a short break?
Yeah, up to you. I can continue or I can stop. Whatever you prefer.
Okay, for me it's okay. We can stop for 10 minutes.
Yep. Maybe 5 minutes, okay? 5 minutes.
5 minutes is okay.
Yeah. Because then I can finish the lecture then today. Yeah.
Ah, okay. If you finish the lecture of today, so we can.
No. I don't. I will not finish everything. One lecture today. I will have tomorrow also.
Yes. But we planned 2 hours for your lectures.
Yes.
For your lecture today. So if you finish,
I will need 1 more hour today. Yes.
Okay. No. Okay, Professor, it's a short break after we started the last part of the first presentation of first lesson.
Yes.
Yeah, okay.
Okay.
5 minutes. Yeah.
5 minutes. Yeah.
Okay.
Thank you.
Thank you.
Poi non so come parlare.
Ok, adesso è attivato l'audio. Può parlare, la sente.
Hi, could you hear me?
Sta vedendo questa è la telecamera. È duplicato lo schermo, cioè sono esteso lo schermo. Vedi, la sta vedendo di schiena.
Vabbè, scusi, mi vede di faccia, ma io non
Sì.
mi vedo, però mi vedete qua. Dai.
Can
Okay, could you hear me?
Yes, please.
Yes, we are waiting for people in the room. So now we can start again because they are here. Please.
Okay,
continue.
thank you. I will start now. Thank you so much.
Okay.
Hi everyone. So welcome back after the break. And as I said before the break, I would like to use 2 lectures, lecture 1 and lecture 2. So the first lecture would be coupled multiscale modeling for understanding failure behavior of natural fiber composite material. As I said, we have got 2 lectures. So this is the first of those 2 lectures. So let us talk about that now, what we are going to focus. Now the focus is we want to understand the damage behavior, the failure behavior for our natural fiber composites. Okay, and this is important because in many applications, particularly in Australia and in New Zealand, where there is a strict regulations on environmental effects of material disposal and recyclability of the material, we are stressing significantly on renewable sources. Now, when we use renewable sources, it's easy to get those sources. For example, we are using a fiber reinforced composite have got fibers and matrix. So fibers, we can use a biodegradable fiber like flax, hemp, jute, any kind of fibers which are stable and could be processed into a fiber reinforcement. For matrix, we could use polymeric matrix like a biodegradable polymer, like a PLA, etc. So that's easy to say we can use those, but when you talk about material property-wise and mechanics-wise, there is complications. The first complication is material property. The material property, if these biodegradable materials are not certain and they vary, there is a huge variability depending on where do you grow that flax, hemp, or jute, whether it's a European, Belgian flax or flax from Asia, or where you grow your jute fiber, whether the jutes come from Asia like India or somewhere else, or if you use hemp, where it comes from, the geography of those fibers, and also the condition of harvesting, and also the seasonal effect can change the properties, mechanical properties, if we are talking mainly for composites, significantly. And that means when we analyze these reinforcements, it is not anymore a glass fiber, carbon fiber, or Kevlar, where the properties are more or less constant or deterministic. So we have to use the variability in our property estimation In this case, it will be modulus, Young's modulus, shear modulus, tensile strength, compressive strength, shear strength, and so forth. They have to be taking into account the variability, and that variability could be high. It is not just that we cannot just use a 3 sigma limit to incorporate that kind of variability in the system. The variability could be large. So we talk about probabilistic analysis. And secondly, if we look at the fibers, a glass fiber is a solid fiber. It has no normally voids, it can have defects, or a carbon fibers are solid. Whereas when we are using this is a cross-section of a natural fiber, this is a pine tree cross-section, a pine fiber cross-section, you could see a very complicated structure with a hollow central area followed by a number of layers. So at that microscale fibers, it has got a gradient in the property and an internal architecture at that scale, which is not present in synthetic fibers like carbon fibers or glass fibers. So when you use this fiber to create what we call yarns, we see very complicated failure mechanics. You can see the hollow fiber being pulled out from the matrix. So we really need to go into the details and implement a very fine scale, sophisticated multiscale method to analyze, in this case, the mechanical response, basically damage and fracture and failure behavior. So this work was done under a collaboration between RMIT University and University of Auckland. And my co-workers are Sam Panamotil, who was a PhD student, and Professor Krishnan Jayaraman, who was a collaborator in this project. And so I'm very pleased to present to this part. Now, I don't need to talk much. We prefer composite because it has got high specific properties, strength and stiffness, and we can easily tune properties, tailor properties for different behaviors. Great freedom of shapes. We can make carved, complex parts with composites like a high-speed boat or a car panel. Now, conventional composites, which uses synthetic fibers, carbon fiber, glass fiber, Kevlar, and matrices, for example, particularly aerospace, we are tending to use epoxies, which are thermoset polymers, which cannot be easily reused, recycled, and they are not easy to deal with for disposal. So, and when these composites for aircraft, aerospace, we still have not much choice. And the aerospace industry, we do need a lot of composite, but it is not very large. But the problem which happens with a non-renewable composites like thermosets and use of synthetic fibers are automotive industry, where we are using volume scale composite production. And it is also important for civil engineering, where we are now using fiber reinforced composite for buildings, for house facades, for building facades, and many applications. So these are large amount of composite materials which just have to be discarded after the life of a car or after the life of a building, and needs to be used in some manner. Safe disposal is important. So as a result, we now have got these regulations, which is ELV in European Union or EPR in Asia, Far East Asia, Japan, Taiwan, Korea, which concerns about recyclability and reuse. And this is the European Parliament directive, which was taken on 2000, so 20 years still over, end of life for various statements. So one solution we adopted in our center of composites is natural fiber composites. So these have low density than conventional composites, good. If these natural fiber composites are used in automotive or cars or vehicles, it has some bonus properties like no splintering during accidents, and we can use renewable source of fibers. So you can grow the fibers every year and reuse again and again. And if you use a biodegradable matrix like PLA or AESO, you can get a completely 100% biodegradable composite like this you see here. However, as I said, the natural fiber, as opposed to a conventional fiber, it poses its own challenges. So if you zoom in to this kind of a pie note showing cell walls, if you look at that in details, you can see this kind of hollow region and this kind of a layered structure using that. So, and this part, so there are different names. So this ML part, which is the area between the two, what we call the fibrils. So this is a fibril, and this is the next fibril. And between that, we have got this called a lamellar structure or middle lamella. And then we have got the P area, which is the primary wall, and then S1, S2, S3, they are secondary walls. And what we normally do, we combine the primary wall, which is P here, which is the blue line, with the middle lamella to call them what we call combined middle lamella. So this is the first point of internal architecture or internal scale within the fiber, and that affects fiber strength, fiber fracture behavior, and damage behavior in the fiber. So that's where the complication starts. And in automotive, we can't ignore this natural fiber composite. They are used in many places: seat backs, coupons, door liners, in instrument panels. As you can see, in a luxury car, in many places there are natural fiber composite. Even a lot of European car manufacturers, German, Italian, they are also using a lot of natural fiber composites. And we can see these fancy cars like Lotus Eco Elise. You can see these frontal exterior panels were made with hemp, which is a fiber-based composite. Can you believe it? This is a load-bearing structure. This has to be certified for crashworthiness, and still this composite, hemp composite, which is a natural fiber composite, was passed and designed and used in the frontal panel, which would need to satisfy crashworthiness. In the event of a crash or accident, this will be subjected to high level of high-speed impact load. That means we need to really use these composites in the next generation. For coming 50 years, these composites will gain more and more popularity. But the challenge is, we have the composite on the right, and if we take 1 yarn out, the lowest level is a yarn, which is a number of fibers impregnated with resin. Now, these yarns are used to create fabric. This fabric is impregnated with the resin to create the composite, and there is the multiscale effect at each level. So in our project, we have used a 3-level multiscale model to analyze this natural fiber composite. But before you apply any kind of multiscale model, what do we need to understand? We need to understand why we are doing the multiscale model, to model the failure. So our objective function in this case, to understand failure behavior, so we can redesign a composite parameter, composite layup, fiber volume fraction, a fiber type, matrix type, so that we could reduce certain modes of failure. We could avoid certain modes of failure. So to understand that, we need to understand what are the failure modes in a natural fiber composite. So you could see here, if you follow my cursor, we are seeing at a scale of 100 micrometer in microscale, looking at fiber breakage and transverse ply cracks. Then we are looking at same scale delamination cracks. These are delaminations within the composite, natural fiber composite. And finally, fiber breakage. This is a fiber breaks, you can see, and fiber pull out, which creates this hole. So the interaction between these multiple modes, fiber breakage, transverse failure, delamination, fiber pull out, etc., requires the complex process zone in the context of a damage mechanics or cohesive zone. If we talk about, if you are using a cohesive element approach or cohesive zone approach, a cohesive surface approach for modeling these damage and fracture problems. So the interaction between processes would be a complex zone. So our cohesive model or cohesive surface model needs to accommodate this if we are using a discrete fracture mechanics. If we are using a continuum damage mechanics, then we need to have these process zone parameters to be able to accommodate these variables. So this is the physics. So we look at what happens in reality, and based on the reality, we develop what we call a physics-based model. So the physics is directly incorporated based on what we observed in reality. So these are the different failure zone. Now, let's focus on a fiber. And the fiber is composed of a number of fibrils. I've showed you before the cross-section of a fibril. And you could see, even at a fiber level, you can see we can get fibrillation. Fibrillation means if you take a fiber and if you squeeze, like I'm doing with my finger, I don't know, you can't see me possibly, but if you squeeze a fiber, you'll get the fiber will degenerate into a number of small fibers called fibrils. So that is what quite often happens in natural fiber composite. Then we get very microscale fiber tearing. So these are the fiber tearing effect. We get the fibrils, fractures, and we also get transverse crack. So these are the fiber axis. We get cracking, which propagates in the transverse direction. Now, all of these happening at a fiber level, and the fiber level damage model, which we use in glass fiber, carbon fiber, doesn't take into account any of this. Okay, so there what how the multiscale model comes into picture. So now I will give you the step-by-step approach we go about and developing the multiscale model, and depending on how much we cover today, I could continue and talk more about this in the next lecture. So normally, when we model a composite, any failure analysis, we normally use macroscopic failure criteria, which does not take into account all the physical processes at lower scale level. So we use maximum stress-based criteria, maximum strain, psi-U, Haseen. These are widely used criteria we use. And they do not take into account all the scale effects. So we can use those, or we can use the fracture mechanics, which I prefer, using interface delamination damage using cohesive models, or what I like to use damage models, which is progressive reduction of material stiffness, and using a number of state variables, which are embedded within damage parameters. So our multiscale model will be representing 3 scales, 2 or more, in this case 3 scales, applied to this hierarchical composite, and we'll use both fracture mechanics, so cohesive model, as well as continuum damage model. So this multiscale model has got a hybrid approach to model the failure. Both cohesive model, which is good for modeling interface failure and delamination, will be used, and embedded one of the scale would use the continuum damage model. Now, when you do multiscale analysis, there are many methods to do multiscale analysis. So in this case, for this composite, we have adopted, my first lecture was on Meschless method, but this was based on a initial Meschless method, but the next level, the composite level, when we zoom into fibers and fiber architecture and matrix, we used double mesh or dual mesh based discretization using superposition methods. So global local mesh, which is using on the background mathematical homogenization for transferring one scale effect parameter to the next scale. And we have used, since this was a project where we need to really analyze, we doesn't need to just formulate it, we need to analyze for real structures. So we used a method which was numerically implemented in a parallel processing algorithm using domain decomposition technique. So basically for multiscale computational technique, we used FE square or FE2 method along with computational homogenization. So that's the approach we use, and some of these approaches has been used a long time, including Fail and Chabot, 2000. So they were the concepts we took some of their concepts. So in terms of discretization, we used a global mesh, and then we use a gradient evolution. We calculate the deformation gradient over each element here, and based on the deformation gradient, we used a wedge splitting method to create in some of the elements a further localized FE. So that's called FE2. One finite element model is superimposed on another finite element model, and the global displacements in the global FE model is updated from the local model. So we used a displacement-based formulation because I would like to clarify this composite, natural fiber composite multiscale damage model work was based on static or quasi-static formulation. So we didn't have wave propagation or dynamic fracture for this problem. So we could use two FE models on top of each other with a global local mesh superposition and using the deformation gradient for global element to the local, to analyze the local boundary value problem using the deformation gradient from the global model. And then in local, we analyzed again. So this shows how we used different domains using domain decomposition method with parallel computation. And you could see in the domain decomposition, we had a code domain, and then we had what we call the handshake region between different domains. So these are denoted by omega E dash and omega, which is the internal domain, which you can solve parallelly. And there's a handshake zone where you transfer. So handshake zone is an overlapping zone where you transfer the variables from one domain to the next table, which ensures the continuity and connectivity between different domains. So this was the numerical method side of this problem. We split into connected subdomains, the whole domain. Then on the multiscale, we have got two options, as I said. These are the intrusive options, means you can use two meshes, local global superposition, coupled with mathematical homogenization, and then apply domain decomposition technique. We did that, but that could make the problem if you are solving large models. If you are solving on a laminate or on a lamina model, like a plate, like a panel level, like a coupon, you can handle the computation well. But if you are modeling a prototype, which we needed to do because this project was sponsored by a New Zealand government in a Ministry of Environment, Ministry of Industry from New Zealand government, we needed to take into account that our multiscale tool should be able to model reasonably larger components. So we used non-intrusive methods as well, which is multiscale computation method and FE2 method, FE square method, what we call, and computational homogenization. So this tells you, so I will illustrate you one of the approaches we used, where we used a number of things, where we use, say, Bishop-Hill relations, integration point. One FE model is embedded within another FE model, where the integration point or Gauss points triggers the next level model from the macro model. So what we did here, so we had a global finite element program, which uses the global mesh, or what we call the Macroscale mesh. And we analyze the structure. In this case, we perform a static analysis using damage and plasticity. And we go through an integration point loop. And within the integration point loop, we evaluate the deformation gradient from the macro model. And we pick one of these RV scale to analyze the microscopic response. So what we do, this is the macro model. We compute, use that gradient, and we pass that gradient for this RV, which is the micro mesh. So which is to this model. We use the deformation gradient from the macro model and pass it here. And we use the deformation gradient to implement a localized boundary condition. So then we solve this boundary value problem within the RV, which is x minus x f macro. This comes from the macro model, and this is the local RV parameters. Then what we do, we solve this problem using an FE model with microscopic RV mesh. And then we can compute based on this kind of Bishop-Hill homogenization technique, sigma stress and sigma bar RV and S bar RV, which are the stress field stresses and strains and deformation gradient, which we pass back to compute the macro stress and the macro quantities, which could be modulus and which could be stress, which could be strain, which could be any state variables of interest. And that is then passed back to the next, the global model. So this was a kind of a two-scale implementation we have used to analyze between macro and microscale in our computational, multiscale computational technique. Now, how we dealt with microscale, which is the natural fiber scale, to the mesoscale, which is the ion scale. So we have used what we call a theoretical and analytical model. So we developed an analytical model to analyze a fiber, which is composed of a number of fibrils and which is having this structure. So what we assume this shell to be a carved shell with a central hollow area. And we model this, the middle lamella and the primary wall as combined middle lamina, CML. Then S1, S2, S3 are modeled in with proper helix angle. We are modeled as 3 plies, equivalent to 3 plies or layers, with the thickness matching the thickness of this. So you can see S2 is quite large, so S2 is large, S3 is small, S1 is small, and CML, which is the combination of middle lamella and the primary wall, is called the layer. So now we have used, you can see the different angles it shows, because the natural fibers, these walls are not straight hollow. They have a helical angle. They act like a helix. So we have to incorporate the effect of the helix or helical geometry along the length, which is the perpendicular to my mouse or perpendicular to this slide or your screen. So we then developed a composite analog, laminate-based analog, to create a CLT, classical laminate theory model, for this hollow fiber with multiple laminas. And these are, we know, lignins or proteins, basically, which create these fibers. So in microscale, another issue we had to address is interface versus interface. So we had, and we know the interface versus interface. Interface with the P means we have a small layer between a glass fiber and a polymer, and this part shows glass polypropylene interface. Okay, so what we found, what the interface with the P allows you to do, to allow the continuous variation of your fiber property to the matrix property, rather than using a step function or sharp change or discontinuity in the property, you could create a continuous variation of property between the fiber and matrix. However, in our problem, when we have a natural fiber embedded in a biopolymeric matrix or biopolymers, or in this case, the work we have shown, we haven't used biopolymer, we have used polypropylene, which is a thermoplastic matrix, which is renewable, which is recyclable, but it's not it's not biodegradable. So we used a simplified assumption. We have used the interface model. So we have modeled a discontinuity in property between the fiber and matrix. So the objectives and outcomes are, we tried to develop models at each scale and scheme to link them. So we developed the model, link different models together with certain variables we identified. And this is quite challenging because this is a practical real material system where we have to incorporate all the real parameters, variable, test data, etc. So one side of this was the model development at microscale, mesoscale, macroscale, and linking them in 2 ways for each scale. The other side of the story was, how do we test at each scale to determine the relevant properties we need at each scale, and how those properties are evaluated at each scale. So we have developed design tests at microscale, mesoscale, and macroscale to determine the properties we need. And then finally, we had to design some tests to validate or verify and validate this overall package of this multiscale framework comprised of micro, meso, and macro model. So the challenges was variability in geometry, as I said, variability in property for natural fiber, the geometry at a fiber level quite complex because each fiber has fibrils, and then we use a number of fibers to create an yarn, and how do we implement homogenization for each scale. So the outcomes, what we found from this multiscale model will be, we have come up with a Weibull distribution, which is, as I was talking about, to account for the variability of fiber properties. We have derived a Weibull distribution to calculate the fiber properties and stiffness for flex fibers. Then we have implemented a fiber polymer interface model to model the damage between the fiber and matrix. Then we have developed a model to calculate numerically evaluated damage for impregnated yarn. So you have got a bunch of fibers, which is a fiber yarn. You dissolve that in matrix, and the matrix kind of penetrate around the fiber to give you an impregnated yarn. And finally, we come up with a multiscale framework for natural fiber composite, or NFC. So in this work I am reporting, we have used Belgian FACS, this is the scientific name, Linum Usita Simum, which is unidirectional yarn fabric. And then we have used polypropylene as the polymer and epoxy. Epoxy is not really a great choice, but since we have an interest of aerospace application of the natural fiber composite, and in aerospace technology, the epoxy is the way to go. Although epoxy is not a good choice to be used in natural fiber composite, but because of the enhanced properties, the strength and stiffness it provides, it is a very favorite material for aerospace applications. And we had decided to evaluate epoxy with natural fiber as well. So these are the epoxy and polypropylene we used for our sample preparation and our analysis, and you can see some. So this is the key thing I would like to describe maybe today, and I will start off today with that, and maybe we can continue tomorrow to look at different aspects. So it's a 3-level model. Microscale components are fiber and interface, and fiber has got fibrils. Mesoscale, when you have got the fibers and you take a bunch of fibers, impregnate with resin, you get a mesoscale property where we are looking at our focus of attention is an impregnated yarn. So a yarn which has got a number of fibers impregnated with the polymer. And finally, at the full composite, we are analyzing at the macro scale. So, and for each side, you can see for the, so this is the fishbone type approach, fishbone type demonstration. On the upper side, you could see we talked about different models. We are looking at different scales, okay? And on the lower side, we have put together physical tests and mechanical tests we have devised and we have performed at each level, micro, meso, and macro, to either determine the properties we need for these models in micro, meso, and macro, or to verify and validate our multiscale model at different levels. So first part was a microscale where we had used an interface normal strength model to analyze the fiber matrix debonding. And we have used fiber analytical Weibull model to incorporate the fiber property variability depending on the flux intent. And we have used a microbond model to compute the interface stiffness and strength, which is to model debonding or pull out between the fiber and the matrix, which is a common mode of failure. Now, to solve this microscale model, we have devised a number of microscale tests, like a microbond test and physical test, to determine these parameters. So we have done single fiber testing, we have done fiber matrix interface testing, and so on and so forth to get the microscale model. So microscale model will provide data for the impregnated yarn to my mesoscale. So when we go to mesoscale, we have two models. One is impregnated yarn models, which is a number of fibers impregnated with matrix or the polymer. It creates an impregnated ion. So, and we are looking at those impregnated ion models at that scale and ion-based RV models as well. So we have done impregnated ion, test of the impregnated ion to determine the mechanical properties we need for the model. And finally, we looked at a macro scale where we have incorporated the meso model input to multiscale models. We did a number of mainly tensile tests, uniaxial tensile tests to determine the stress strain response, which is the stress strain curve, which provides you the modulus and failure strength, and compare that with the macroscale model analysis, FE analysis with the multiscale model. So I will now going to describe in a bit more detail of each model before we close off today, because I know there is other presentations coming by. So let's look at the microscale today, how the microscale properties were implemented. So microscale, we had fiber and interface properties is our key property we want to understand. And we did fiber test and we did microbond test. So fiber test to determine the fiber properties and microbond test to determine fiber matrix interface properties. We have used analytical and numerical models. So we use microbond models, interface normal strength models, and fiber models. And all these three models, this gives you the fiber properties, this gives you the microbond models, microbond properties, and that gives you the interface normal strength properties. So we did fiber test, SFTT, single fiber tensile test, SFTT, where we take a fiber and we look at 4 gauge lengths because the fiber property varies. These are natural fibers, and we have to create a probabilistic distribution, in this case, a Weibull distribution of fiber properties. So we measure at 4 gauge lengths the tensile properties of the fiber, and this is an equipment we designed specifically for testing a single fiber. You can see this is actually a paper which is fixed with two jaws. This is like a tensile machine jaws, and this is one fiber. So you pull this up, you fix one jaw, pull this up, this applies a load on the fiber, and finally fiber breaks. So you can get a stress strain response and you can get the strength of the fiber. Okay, so this is to determine fiber tensile property. Then we have used torsional pendulum to determine fiber shear. So I'm going to present this because this is not just only a numerical or mathematical development. Yes, the mathematical development of the model is accompanied by consistent experimental test, because many places these properties we kind of take from literature and all we assume. And that doesn't work if you're designing a real material system. You have to get these properties from real test. So we got the shear properties. Then we did a Weibull plot between the log-log plot between X and Y, and we calculated this median rank, which gives us a representative fiber property index. And that comes through the correlation coefficient, and these parameters basically R and N, where we get plot of X, which is the log of the value, which is the fiber tensile strength or shear strength or modulus, and Y is log 1 by median rank. The next level, after we deal with fiber, was fiber matrix interface. Now, fiber matrix interface is a very, very difficult test to do, and the test standardly we do called a microbond test. So this is the fiber, and you put a drop of polymer around it. Okay, so this is a blob of polymer or the matrix, and you have the fiber. So what you do here, you pull the fiber. So you hold this blob like this micro blob, you can see between 2 supports. So these are fixed supports, and this is the fiber, and this is the polymer blob. Okay, now you pull the fiber, so you get a shear, and this small piece comes out, and the fiber ultimately fails at the interface between the fiber and polymer. And then you can get the fiber pull out. Okay, fiber pulls out, and then based on the loading, the load at which the fiber pulls out, you can determine the interface strength. Then what you do for the fiber, that was the strength, fiber strength, this is fiber strength, and this is about the interface strength, then the stiffness. So we need basically modulus and strength at every scale, right? To get the engineering stiffness, we use the Halpin-Tsai model, where we have used this type of composite laminate model for the, like I showed you, the cross-section of each fiber. So it starts with a middle lamina at the lower, primary wall, secondary wall, 1, 2, 3. Finally, you have a lumen. And you transform these to a typical conventional composite equations with using the rule of mixtures and classical laminate theory. You determine the constants like E11, E22, G12. So E11 is the tensile strength, E22, G12 is the shear. But you have to understand, this is not a flat plate. It is a best approximation. It is a circular annular system with different thickness, and each annular layer has an helix angle. So like, for example, S2 layer has got normally helix angle about 10 degrees. So we have to include the helical angle effect and develop a modified composite laminate theory for an annular cylinder with the helical angle included. So a new Halpin-Tsai equation was used, but they were modified for the helix angle and CLT to get the fiber stiffness property. And then for the interface, damage law, which will be embedded in the microscale model, we used models like Cooper-Kelly, Shear-Noreen models, and combined and implemented with FE models like cohesive surface matrix interaction. So we implemented a cohesive model between the fiber and the matrix. And the cohesive parameters, how did we determine it? We did determine the cohesive parameters from the microbond test. And then we can plug into this cohesive property sigma 0, tau 0, which we determine from microbond test and in the FE through a quadratic damage criterion, where this comes from, or this is verified using a known analytical model like Cooper-Kelly and Shear-Noreen models. So that helps us to determine the property between fiber matrix interface, the stiffness and the damage using a microscale, using these models, cohesive surface and quadratic damage criteria. So that completes the microscale. And next we looked at what we did at mesoscale. So at mesoscale, our focus is impregnated ions. So we developed ion RV models and we did test. So what we did, we have developed a single impregnated ion model, which uses fiber, interface, and matrix properties. And we impregnated ion models were based on single impregnated ions. So one ion with impregnated matrix, using the fiber matrix interface properties, we developed at the microscale, we developed an impregnated ion RVEs. So impregnated ion RVE means multiple number of ions. So we had a single ion, classical laminate theory model, which we presented here, right? We use that in the model to get an impregnated ion model, CLT model, impregnated ion models, and RVE models together at the mesoscale. So it's a focus on ion. So fibers were modeled using CLT with the modified helical equations that is then implemented within, including the matrix around the fiber. So impregnated ion-based CLT model. This doesn't have matrix. This is impregnated one fiber with matrix. Then you combine with a number of ions, impregnated ion model to create an RV model at mesoscale. We have to do tests to get parameters at mesoscale. So we did this test where we had impregnated ion tensile test, both for flax polypropylene material system and flax epoxy. Flax polypropylene specimens were prepared by compression molding and flax epoxy prepared by resin impregnation. And we did the tensile test. How the tensile test was done, we used a heated plate, 2 Teflon sheets. So this orange are Teflon sheet, the gray is heated plate, and we put polypropylene sheets here. Okay, and then we have got ions on top of this. This is how we manufactured using compression molding flax PP. And for flax epoxy, epoxies are thermoset. So we use iron here, fiber iron. We use 2 vacuum bags and with a glass base, to vacuum bag with a glass base, and we use a steel plate to manufacturing our sample. Then we went ahead and created the single impregnated ion model, which includes the fiber dimension, which can change, fiber properties, interface properties we have calculated before. And important to see, in a normal plane, you have got the multiple fibers, right? You can see in a ion, this is the shape of a real ion, which is like a bent carved surface. And this ion has got many fibers with matrix. So you can see this, this is a multiple ion. You can see all the single ions inside the normal plane, the tangent vector, and the helix curve. So we included this helical angle for individual fibers to come up with a combined or integrated helical impregnated ion model, okay, which takes into account fiber dimension variation, fiber properties, interface properties, everything. And then we used impregnated ion RVE, where we use this to create an RVE model based on single ion, and our orientations were calculated based on the helix angle. Again, I can give you more details, mathematical formulation and all. If you need, I can send you the papers. All of them have been published. We use voxel mesh, periodic boundary conditions, and to create a numerically estimated damage law for multiple ion models or impregnated ion RVE. Finally, we came up with a numerically estimated damage laws, which you can see how the impregnated ion was modeled in 1, 2, 3 axis. And finally, we assemble this impregnated ion in a number of layers to create a fabric composite models, okay? And we used a compaction simulation to make sure the fibers just touch each other, and we take into account the fiber orientation using 1, 2, 3 axis. So this is a compacted ions, then impregnated with the matrix, of course. So we create a fabric model from the RV, impregnated ion RV model. We come up with a fabric composite model. So we assign orientations to ion elements. Number of layers are corresponding to the composite. So number of plies would be equal to number of layers. We simulate the compaction between the fibers and orientation assigned to ion elements. So that completes the mesoscale model data. And finally, the last thing remains, the macroscale model, which I believe we need to wait for the next lecture, where I will cover the macroscale model, and then I will show you the results, which is coming up in my next part, which is due tomorrow. Because we have reached the end of time for today's lecture, I would like to thank you very much for your time, and I'm sure I'm looking forward to seeing you all tomorrow again. Thank you very much, everyone, all students, all professors, all teachers, and particularly Professor Patricia and her team.
Di andare ad analizzare la modellazione 3D applicata tra tunnel, terreno e struttura, applicando dei modelli costitutivi che siano realistici e appropriati per il terreno e anche per gli edifici storici.
Devo parlare di Devo parlare qui perché quello sta acceso. No, non era l'esame del dottorato.
Però sì, mi senti da qua, perché ha l'audio acceso di Zoom.
Sorry, Professor Rajdas.
Yep.
I have a question.
Sure.
First of all, thank you for the presentation. It was very clear and interesting. I would ask how much the computational effort of this model is affected by the microscale.
It depends on how much detailed microscale physics you incorporate. It depends on how many micro RV you choose.
Okay.
So micro RVs, we can't choose for every element and number of micro RVs. We have to choose based on the sampling, the probabilistic model we use. So if you use more micro RV, your model will be more accurate, but it will increase your computation. So normally, but the good thing is we have used a quasi-static analysis in this case. So we could manage with the nonlinear simulations, with a nonlinear iterative solver. So basically, some of our simulation we ran in our supercomputer in National Computing System in Australia, which took maybe 3 days to run a complete a small scale component, maybe a small scale aircraft component or automotive component. Took 3 days. Some of them where we really wanted detailed model took us even a week.
Thank you. I have another question.
Sure.
It was really interesting how the microscale properties have been tested with brand new test on fibers, and we also know that wood is a living material, and is sometimes affected by moisture, environment, and how can we deal with this problem?
Yeah, look,
and
this is a real question.
Is it possible to integrate a diffusion model for the water?
Yes, sure. So what we are doing another project with Defense now, where that is not multiscale modeling, and I'm supporting the project. The problem of the project, or the objective of the project, is to create envelope property data with environment effect, moisture, temperature, and even UV exposure to this material. If you use in aerospace, because this aircraft goes in an UV atmosphere and they execute thermal cycling, okay? So high temperature, low temperature, landing, takeoff, right? So we are creating the map of property with these environmental conditions, and we want to implement that within our multiscale model. But getting property at fiber level is very challenging. The model is as good as the input. If the input is not good, the model predictions will not be good, right? So we are doing a lot of tests to get high quality input data, both within our lab and also in the literature. And we would like to collaborate in this work with Sapienza University, with Professor Patricia's group and her other co-members like Professor Fantuzzi, Dr. Pingaro. They have been very helpful. So I should have been in Italy now, but due to lockdown, I have been present in Melbourne.
Okay, thank you very much, Professor.
Are there any other questions?
Yes, I have a question.
Okay.
Thank you.
Please,
Sure.
Ray, I
Thank
want
you.
to introduce you, our postdoc researcher, Raji Zadi from Iran, that is involved in the work of our group.
Very nice
Thank
to
you
meet
so
you.
much. Very nice to meet you too. Thank you so much. And thank you so much for your great presentation. It was really interesting to me. I had a quick question. For a multi-scale model, starting from atomistic simulations, for example, molecular dynamics simulation, to micro and mesoscale, where should we get the damage criteria? Should we get it from the atomistic simulation?
Okay. First, I will answer this question by telling you have to define damage at an atomic scale. What do you define as a damage to be? When you are doing atomic scale, you are starting with an ordered system. So atoms and molecules which are in order and which perhaps is in equilibrium. For example, if you are modeling metals, you are looking at atomic crystals which are perfect, but then you are including the defect. For example, dislocations, which are sliding defects within the materials, which causes plastic damage. So you have to relate your damage definition with an atomistic parameter. For metal, it is dislocation density, which I have used. I have got a number of papers I can send you with the damage variable. For composite, we have, say, the polymer have got these polymer chains. So you will use an atomistic scale simulation. Probably molecular dynamics is not very good for polymeric chain. I would recommend using Lattice Boltzmann, which is a semi-continuum method to model this chain. So if you look at an average, so if you say my damage is defined as the average number of polymer chains which are broken, then you link that damage variable with a broken polymer chain, which you can model with a potential function at a Lattice Boltzmann law, Lattice Boltzmann system. Okay, so what I'm trying to say, you have to find atomistic parameters and define a damage which is linked with that. And you define as a scientist in that case. And then you can do a micro and mesoscale level. You can't do macro, it is too difficult, but you can do up to meso and micro level, yes.
Sure, thank you so much.
Thank you.
Any other questions? Majid, please. He is our new PhD doctor that will join us in November, maybe.
Okay, good. Good luck.
Majid, what do you think when we can meet?
Professor, I think there's a problem with Majid's microphone. Maybe it's better to talk with my microphone.
Okay.
Just a moment, please.
Thank you.
Okay.
And also, you know, I'll be really looking forward to collaborate with some of the students, you know, later on.
Sorry.
Okay.
I want to thank you, Professor Das, for your excellent presentation. I'm now really interested in all of the materials you provide. Although that's a lot for me now.
I can give you all the papers. I have got a bunch of papers. I have a set of reference I can send to you. If you write to me, my email address is given. So you are feel free to talk to me, write to me, you know. I can talk to you later on, no problem. I like interacting with PhD students because you guys are the next generation scientists, right? Not us.
Thank you.
We are getting old and we are not, we want you guys to come up.
Yes. And maybe my question is somehow basic. When you were talking about the SPH method, everything was nice, all benefits, all goods, everything was good. And the question arises was why we are using FEM method. For example, correct me if I'm wrong, in this Macroscale, in the last slide you were explaining, do we use the SPH or
No,
just
it's all
FEM? FEM,
yes.
And the question is why we are still using FEM, since you said that.
I will tell my statement again. I have highlighted some advantages of Meschless method for some specific problems when you have discontinuities, when you have large deformation, when you have fracture. These things are difficult. These physical processes are difficult to capture with FEM. That's why I have used SPH for those problems. Now the SPH has got a lot of good things, but there are also certain disadvantages with SPH. One is the SPH formulation, if you want to use for correct formulation, which is called a consistent moment, that is CSPH, which corrects for when you have a fracture or large deformation, these particles get disordered. They don't remain in a regular spacing, and that will create an error in your solution due to that disorderedness, which we can correct it using consistent moment. But the consistent moment has got to do with an inversion of a local matrix problem for each particle interpolation. That will add significant computing level for you. So I haven't gone in that detail, but I can explain. So that's the key thing. If you can use SPH, but you don't get any benefit of SPH if you are solving a quasi-static problem. Unless you are solving discontinuity, large deformation, there is no benefit. Now, FEY, which is popular, it has been being developed for last 40 years. We have a lot of commercial software, like we have integrated our FE code with Abacus, ANSYS, which you can use a lot of facilities, which we have not developed with Meschless. That is the way the technology has developed, the computational technology. So to go with the technology, FE has become more popular. And for this problem I am showing you, SPH doesn't give any advantage. But the fracture problem I showed before, the dynamic problem, large deformation fracture, SPH, Meschless method has advantages. And that's why we use it there.
And can you give me a measure of how time consumed for the numerical calculation?
Yeah, look, that depends on how details you want to resolve, as I mentioned to
for example,
you know, yeah.
For example, in a solid and fluid interaction problem.
Yeah. So time consumption depends on how fine mesh you use and how is your gradient you want to, because your resolution will determine to capture the gradient, right? So depending on the gradient you have, that will determine your computation time. But with SPH and FE, there is no advantage of computation. SPH can be as computationally inefficient as FE. It may need the same time as FE. So the advantage of SPH is simulating discontinuous large deformation transient problems.
Non-linearity.
Non-linearity, yes.
Yes. Thank you.
And strain rate dependent equations, etc. Yes.
Thank you so much.
Dear which is the right pronunciation of your name?
Raj, R-A-J.
Name and surname.
My first name is Raj, R-A-J.
Das.
And Das is my last name, D-A-S.
Okay. So, Professor Das, we thanks you a lot for your general lecture that amaze all of us with the very wide variety of applications of multi-scale computational methods. And I think that our PhD students and other participants can have the opportunity to know the worldwide state of the art of research on this matter, that is multi-scale modeling of composites. And yesterday they know the essentially mathematical point of view of the school, the French school, and the other approaches. And I think that the merge of all these approaches could be useful to understand the phenomena at all. I just want to ask you for two questions that to which I like to dedicate attention. The first one is if you ever consider the possibility to investigate behavior with size-dependent, size-informed continuum models like non-local models. And in case, I think that we can maybe work in this direction together.
So I know from, yeah, sorry, yeah.
Yes, please answer.
No, I know, Professor Patricia, your work on this, very, very well-known work, particularly because of the fiber matrix damage model. We would like to use your approach of non-local damage. I have started working on that, but I need your help and collaboration from your end to be able to do that. Yeah. Okay,
and the other question concerns the of course, possibility to study materials with random microstructure, because in this case, the RBI is an unknown of the problem. And I will try to show something about this, but I think that the homogenization applied to random materials could be of important, could give important outcomes in the applications to materials with microstructure, with not periodic microstructure. Because I think that you use normally RV defined in
we are working towards we are working towards implementing random microstructures, and we are following the research of your group on that. That is very important because, as you know, these fibers don't have a deterministic dimension. Every fiber is of different diameter. Every fibrils are of different type. They are of different properties. So it is really a complicated problem, much complicated than what I presented. So I think we need non-local for fiber matrix resolution of the deformation and damage mechanics. And we need the random continua models, which would be a better model than the Weibull model we have used, which is a statistical model, but we can replace it with a random continua model to improve this.
Yes, in our case, only the microstructure is considered random and the continuum is
okay, fantastic. That would be great. Look
generally a
forward to
non-local
collaborate with you.
continuum. But we will talk about this.
Thank you so much. Thank you very much.
I think that if there are not any other questions, we need to do in any case a break, and I will start my lesson at 12.
Okay, thank you very much, everyone.
Thank you very much again, Alai, and see you tomorrow.
Ciao, 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 ciao.
Ciao.
See you tomorrow. Bye.
Which time is in Australia now? Microphone. Switch off.
8 o'clock.
Okay. So have a good dinner.
So it is the dinner time for us. But I wish if we have pizza and lasagna.
No, I don't know. Sorry, Professor, I don't understand.
No, we will prefer pizza in the dinner. We will prefer to have dinner with pizza. Pizza.
Ah, Pisa.
Pisa. The city.
Yeah. Okay, see you then. Bye-bye.
Okay, bye.
Bye.
No, io non ho capito. A specific step of the lesson of yesterday that is related to the presentation of the multiscale and multiphysics modeling for complex materials group. And moreover, I want to remember that I started my lessons with the mention to the definition of complex materials and with a glance to generalized continua. And I also highlighted the impact of all the ideas that was derived by the molecular approaches of 19th century of the molecular theory of elasticity by Navier, Foyt, and Poincaré. And I focused the attention on the possibility to use the approach, for instance, of Foyt to refine the molecular, the discrete corpuscular micromodeling for deriving suggestions and criteria for continuum scale dependent modeling. And as I said in the last session, to have a continuum size dependent, that is with size in the field equations, means to have a non-local, in that case implicit non-local description. And what I want to just remember is that in my definition, complex materials is a material with internal structure that can be detected at a very different scales level. And the multiscale modeling, you have a presentation of Professor Ibrahim Begovic yesterday and Professor Raidas today, is generally conceived as the dialogue among different material scales, starting also from atomistic, as you said, and in the questions of some of the participants. But normally very often it is sufficient to consider only two scales, and this is the case that I analyzed. I don't know why marco questa parte da solo. And in particular, the starting, the description of the material, let me say at a fine level, is conventionally called micro modeling. And you can see in this slide that the micro model has a microstructure that can be defined at different length scales. And through some equivalence, for instance, in terms of energetic equivalence, we derive, using some techniques, the continuum, the relations, the constitutive relations of a continuum macro model, which preserve memory of the microstructure. And I want to focus the attention to particular micro model in which the memory of the size is preserved. And we yesterday analyzed a wide variety of micro models that are defined as non-local, that is size dependent. And today I want to show you some example of macro model modeling. So, just in particular, it is known that the presence of material internal length scales can be accounted for by direct discrete modeling with generally high computational cost. What is not completely recognized instead is the possibility of preserving memory of the microstructure by resorting to continuum scale-dependent non-local theories. Okay, this is what I want to say. We can model the microstructure by a direct discrete modeling, or using, this is my proposal, continuum scale-dependent theories that are non-local theories. And let me skip to the second lesson. Spero di non aver lasciato audio in diapositive varie. Perché se è così esco e vado dal PDF. Okay, in this second part of the lesson on multi-field continuum and multiscale methods for the modeling of complex materials, I want to present a discrete to scale dependent continuous model for materials with microstructure. Scusa Marco, ma questo parte da solo. È come se avesse impostato la... remember that the basic idea is, of course, the possibility of describing the material microstructure at a so-called conventionally defined micro level. And if this possibility is guaranteed, this is not always the case, but we can try to do this in various situations. It will be possible to derive a constitutive theory that also using the words of Ericsson, and I am mentioning a book dedicated to the molecular theory of elasticity of 1977, a constitutive equation produced from a plausible model, micro model, I can add, is by one interpretation physically reasonable. So let us consider as a reference material a composite materials made of particles embedded, can be considered rigid, embedded in a deformable matrix. I need to stop just a moment because these slides proceed automatically. I don't want to use this automatism. Please let me stop just for a moment. I hope to be ready. So, let's consider a reference material as a composite material made of stiff particles embedded in a more deformable matrix with distribution of defects that could be pores or microcracks, such as ceramic or metal matrix composite. That is a polycrystal, which can have interfaces that could be grain boundaries or thin and thick interfaces as shown in this slide. And of course, the approach of the modeling of the microstructure could be vary with relation to this distribution of particles inside the matrix. And first of all, focus on polycrystals with the grain boundaries or thin interfaces. That means to consider materials, for instance, like masonry, because masonry can be, of course, considered as a composite materials with interfaces that are can be modeled as grain boundaries. And moreover, jointed systems, that means rocks, for instance, also can have the same kind of description. And also cemented granular materials and many other kind of materials that we can be reconducted to this class. That is materials, if they are metal matrix or of cement or cement matrix composites are polycrystals with thin interfaces. And for such kind of materials, we can consider the particles as in the original molecular models that I presented yesterday of Cauchy, Foyt, Poisson, Poincaré, and the others, can be considered as ultimate particles inside which no forces are accounted for, or are of smaller order than the intermolecular forces. And in that case, I think that it is possible to consider a deterministic distribution of the microstructure. And this means this is obvious in the case of regular textures like in masonries, for instance, but it could be considered suitable also for materials in which there is a high volume fraction. The high volume fraction we can define as the volume of the elements, the grains, the blocks, with respect to the total volume of the a reference control volume. And of course, in the case of thin interfaces or grain boundaries, this condition is satisfied. And in this case, and I think only in this case, it could be possible to define a representative volume element, RVI, name this representative volume element for the future, and perform any kind of homogenization that is related to this periodicity. The second case that I want to present is the case of composites, polycrystals, ceramic or metal matrix composites, or also cement matrix composites, with the so-called dilute concentration of particles. In that case, it is very difficult to avoid the random description of the microstructure. And in this detail, we will enter in this lesson and the other seminars that will follow this lesson. These are other kind of materials in which we cannot resort to the periodicity of the microstructure, and note that for dilute concentration of microstructure, I mean a concentration that is, it is considered a concentration of particle that is less than 40%. And among these materials, we can also consider masonry, but I think that masonry is better represented by the class 1 of a sort of deterministic microstructure. Anyway, in the case of random materials, the procedure of homogenization must take into account the randomness of the distribution of the particles, the randomness of the geometrical distribution. And what will be presented in the lessons of Dr. De Bellis that will follow my introduction, these lessons will be focused on the homogenization for such kind of materials performed using the solution of boundary volume, boundary conditions problems, and these boundary condition problems depend on the definition of so-called macro-homogeneity condition of Hill type that we extended to the case of micropolar continua. In that case, the microhomogeneity condition is generalized to the case that, in particular, Cosserat micropolar continuum, in which you can remember that we have additional degrees of freedom. And the additional degrees of freedom of the micropolar continuum are the rotations of the particles and the stress conjugated measures that are called the couple stress. But this will be detailed in the next lesson of Dr. De Bellis. And in this case, boundary value problems consistent with a generalized Hill conditions, generalized to micropolar continua, can be used, and Dirichlet and Neumann problems can be solved, and obtaining the upper and lower bounds for the values of the effective constitutive terms. You participated to the lesson of Professor Ibrahim Begovic yesterday. He also introduced this is a classic problem of bounds in homogenization theory, and this will be the topic of the lessons of Dr. De Bellis. This is just a schematic of the kind of Dirichlet boundary condition that can be applied to a representative volume element, and the boundary conditions concern displacements and rotations in the case of micropolar case, while the Neumann boundary conditions concern stresses and coupled stresses. There is also a general approach that we like to use to consider this kind of materials. I remember that are materials in which the concentration of the particles can be considered dilute. So less than 40% of particle distributed within control volume. And in that case, what is really unknown, as Professor Martin Ostoja-Starzewski described, widely described in a book of 2006, and I will suggest to consider this book if you are interested in this topic. What Martin Ostoja described, we worked a lot with the Professor Ostoja in the recent years, is if as the the size of the representative volume element in a random medium is unknown, it is necessary to define a procedure for which the unknown are the constitutive constants of a micromodel, but also the size of the representative volume element. So this is a procedure that has a statistical basis, and the idea is can be referred to a procedure of it is called moving window technique, in which you use a RVI of bitentative and then move into a defined domain, this window, in order to find a convergence of the results. Then enlarge the size of this control window and continue the analysis till the convergence. And the scheme is this one. Consider on the in the vertical axis parameter of the material, a constitutive parameter to detect, and on the horizontal axis consider the number of the size of the control window. Then, by enlarging this size, it is demonstrated that the process, in statistical terms, converges to a defined size. And I want just to introduce the lecture of Dr. Pingaro, in which this procedure has been casted into a very fast methods that he will describe in detail, and allow us to do hundreds of simulations with the aim to define the size of the representative volume element for a random material, and of course also the constitutive parameters as results of we can call Monte Carlo simulations for the definition of the constitutive parameters. And this is just to introduce the next lessons. Now, instead, I wish to focus on the first kind of materials that I called polycrystals with thin interfaces or grain boundaries. And in this case, the idea was to follow an approach like the approach that I showed you yesterday, presenting the model of Voigt. Do you remember that Voigt considered a discrete system made of particles that interact through forces and couple? And I want to extend this concept of structured molecules, molecule with the microstructure, endowed with a structure, I prefer this term, to represent any kind of materials. In particular, the material is made, the reference material that I consider is made of rigid, so stiff particles that are described as rigid, and also slit. In that case, using the procedure that I want to show you, but follow the path delineated by Cauchy and Voigt, a multi-field, so a continuum with additional degrees of freedom equivalent to the complex lattice model defined, can be derived, and this continuum retains memory of the fine organization of the material by means of non-standard, non-classical, additional kinematical and dynamical descriptors. This continuum is equivalent in terms of virtual work, or we can also be consider equivalence in energetic terms. But this, the outcome is the same. In the continuum representation, it is better to go into quickly into this detail. Let's consider a lattice model that is made of kind of structural molecules, representing the material internal phases, and the material internal phases could be fibers, defects, void, inclusions, particles, etc. Then the particles can be represented as rigid bodies, while the pores, the microcracks, the microflows can be represented by these elements that I call slit. And what is this slit? The slit is a device for transmitting to the matrix additional forces due to displacement jumps over the actual flaps. Is an additional degree of freedom, as you can see in the continuum description. So consider, as in the models of Cauchy, Voigt, and Poincaré, a generalized form of the so-called Cauchy-Born rule, that is a kinematical, in this case, map that connects the high number of degrees of freedom of the discrete model, so of the fine, let me use the term fine to describe the micro level, and let me use the term coarse to describe the continuum gross level, macroscopic level. So these maps connected these maps can be of any order. In this slide is represented a Taylor expansion till the second order. In this formula are presented the second order gradients of all the descriptors that I introduced. And if we remove the hypothesis of a higher gradient, or that is, if we consider homogeneous deformations that have a fine representation, linear representation, where only the first gradient appears, I can resume that the descriptors in the continuum models the derived descriptors in the continuum models are a standard displacement field, which corresponds to the displacements of the particle centers. A stands for the particle A. Then a micro-rotation field that is, in this representation, a skew-symmetric tensor field, which corresponds to the particle rotations, capital WVA. And finally, an additional non-standard displacement that is a relative displacement representing in a smeared sense the displacement jump that could be over the actual microcracks. This is what I call a complex lattice model. And in the case of homogeneous deformations, for instance, it is possible to write the mean work in the lattice system of the internal actions, and the work of the lattice systems account for matrix and particle interactions, for matrix and the slits interactions. Remember that the slits are representing the microcracks or the ports, and if present, also particle slit interactions. And using the maps, kinematical maps that I presented before, generalized version of the Voigt maps, the power of the internal actions in the lattice systems can be expressed in terms of the continuum fields introduced and their gradients. In that case, just simple algebraic steps could be performed, but the result is the expression of the mean work of the internal actions in terms of continuum fields and their gradients. These continuum fields will be the strain measures of the multi-field continuum. Then, using the localization theorem, we can consider the continuum density of internal power, virtual internal power, and equates this internal density of continuum, the density of continuum internal power to the mean work of the internal actions in the continuum. After some other algebra, we can derive, as I said before, the expression of the internal work density in terms of continuum kinematical fields. And the kinematical fields that you find in these slides are the strain measures of the continuum. In that case, these are the strain measures linearized because I am considering the framework of a geometrically linearized theory. Here you can observe the gradient of WV, that is the standard displacement, and minus the micro-rotation that is represented by a skew-symmetric tensor. And we also have the gradient of the micro-rotation and the additional displacement D, which accounts for the presence of the pores of the microcracks, and the gradient of this additional displacement. All these terms, that this is the dot product, the inner product, the scalar product, all these terms correspond to the identified stress measures. And you can see in these formulas that these stress measures, which are work conjugated to the strain measures, are expressed in terms of geometry of the lattice systems. These A minus B, for instance, are the difference between the position of a block with the center in the point A, and a block with a center on the point in the point B. And T is the interaction between particles, and R is the interaction between slit and particle. This, of course, are composition of geometric vectors. PA is a point in the discrete system, and A is the center of the block A. X is the center of the representative volume element that we choose. So this can be considered as a fabric, vectors, and tensors. Just to have an idea, I don't have time to enter into details, but I want to show you this slide again. Okay, just to show which are the kinematical variables, kinematical and statical variables, dynamical variables that I introduced. A is the position of the center of a particle. This particle is described as a rigid, and this is the displacement of a particle, W, and this is the rotation of a particle, and in that case B is the position of another particle that interacts with A and interacts, like in the Voigt model, through forces that I call here T and couples that I call here P. Then we have also the terms, the elements that I call the slits, which represent the microcracks, and also in this case there are some forces that the microcracks exchange, and the forces that the microcracks exchanged are called zeta I, zeta H, and zeta K, considering a slit centered in position H and a slit centered in the position K. And moreover, this picture represents the interaction that I name R, RB, of course, in the other particle, representing the interactions between the slits, the pores, and the particle. So what is important now is to know the idea that underlines this procedure. This procedure is an equivalence in terms of virtual internal power, and the result is the identification of stress measures. What is important to recognize is that corresponding to additional strain measures, we can identify additional stress measures. In that case, this is the term that I call stress tensor, S, and this is the term that I call sans serif S, couple stress tensor. This is an additional term that I call configurational or material force. Remember the presentation of yesterday when I considered the continua with the fine macrostructure and configurational forces. And capital zeta is the so-called microstress tensors. which is also related to the presence of the microcracks and represent a configurational variable. So this kind of continuum is a continuum with rigid, that is micropolar. See the lesson of yesterday, a continuum with the rigid directors in the sense of Erichsen-Trussell, and an additional deformable microstructure. This microstructure is affine because the deformations that I introduced in the kinematical maps are linear. So the representation is affine, only the first gradient appear. This continuum is presented in the book that I mentioned in the slide by Mogen, but in particular Gertin, that is, in my opinion, much more clear and founded on the basics of continuum mechanics of the Trussell school. And I do suggest to study this book if you find interest in deepening the aspects of continuum mechanics of this kind. And let me remember that this term T, P is the point through which the particles interact. And consider that this point can be defined in a free way, because if you had two rigid bodies in contact, you can select one point. I call this point P, contact point, and then represent the action as the action of a force and a couple, as in a discrete system, system of rigid bodies, a Lagrangian system, if you prefer this definition. The interaction can be always reconducted to the action of a force and a couple. So if you put this point in the center, you don't see the couple. But if you put the point in another, differently from the central axis, you have to put a force and a couple. So this point can be chosen arbitrarily, and unless to define forces that I call T and couple that I call C. And the couple is also identified by the index P, because is the Pth contact point in the system. Of course, we, in a representative volume element, we have a number of particles and a number of interfaces, and then a number of contact points. And these sum are extended to the total number of the particles and to the total number of the contacts. Then look at these formulas. We have here a stress tensor that is identified in terms of contact forces. These are other kind of contact forces representing the forces between slits and particles, and position vectors, what I call fabric vectors. We have now to give an expression. We have to identify the terms T, P, that is the contact force on a particle, or Cp, and in case also Rp. So we have to describe at the microscopic level a constitutive relations for the contact forces and couples of the lattice system. The constitutive identification must be done at the microscopic fine level. If this constitutive characterization is given, and I don't now want to enter into the constitutive characterization that I used for this model, because these are response functions for the contact actions of the lattices that has the role of a paradigm of physically based micromodels, but they can be defined in any case. I will show you when we define these functions for the masonry assembly or for other assemblies of composites, but the key point is that we have to define the constitutive relationships at the fine level, and then the constitutive relationships at the macroscopic level is a result of the identification made using the so-called generalized Cauchy-Born-Voigt rule. And the stress-strain relations that we derived are naturally depends on the constants of the matrix depend on the geometry of the assembly, and what is important to focus is that the geometry means size, and this is not normally true in the case in which the continuum is not non-local continuum, shape, and orientation of the heterogeneities. And in particular, S is the so-called macro stress tensor, while sans serif S, I already introduced it, is the so-called coupled stress tensor. Then zeta is an internal body microforce vector which preserves memory of the microcracks, the voids microstructure. And the capital zeta is the so-called microstress tensor. Before entering into the description of some applications, I just want to frame this continuum that I call multi-field continuum within general, non-linear, kinematic, and dynamic description. This is a continuum with rigid, as I said before, and plus deformable affine local structure. And from a general point of view, in a non-linear framework, we have the standard displacement. Here, the standard displacement is called U. It's represented by the vector U. Then the additional micro displacement that here is represented by the vector V. The sum of these two displacement, macro and micro, is the total displacement UT. Then we also have a rotation. This is a tensor which is included in the system of proper rotations, and the proper rotations are the rotation with the positive determinant rotation in a finite framework. And these are the deformation gradients. This is a schematic of the deformation of the body, in which I try to represent both the deformable and the rigid microstructure. This is the gradient corresponding to the deformable microstructure, and this the gradient corresponding to the rigid microstructure. And in particular is the gradient of the additional degree of freedom of rotation. And the term micro refers to the microstructure. So what I call micro are terms that are additional to the so-called the macro, that are the classical continuum field. These are the defined strain measures, and what I want to show is that this is the same of the first slide, that these measures after a linearization, so by passing from a finite framework, a kinematic finite framework, to a linearized finite framework, do standard expansion with the infinitesimal term called epsilon, we can obtain the previously defined linearized strain measures. With the previously defined, I mean the strain measures that were identified with the procedure of homogenization that follows the suggestion of Voigt. Another point that can be stressed is that in that case, the rigid micromotion that can be defined by these relations to a rigid macromotion corresponds, as in the classical model, null strains, while in the case of the microstructure, so the additional degrees of freedom, to a rigid motion corresponds non-null strains, and this can be explained by considering, for instance, if you consider a body with the pores or cracks inside, if the strain measure is the relative displacement between 2 points of the pores, the terms that I represented with a vector t, if this body with pores undergoes a rigid motion, the pores remains opened, and the strain measures are not null, even in a rigid motions. And we will see what this means in terms of balance equations. So strains not all vanish under rigid motions. The procedure that I want to quickly propose, procedure multiscale multifield modeling, follows these steps. The first step is the work of express the work of the internal actions as a function of tests, that means virtual strain measures, from the discrete continuum equivalence procedure, Voigt-like. Then the divergence theorem can be applied, the virtual work principle to define the structure of the tractions, as we will see, and the virtual work principle will lead to the structure of the internal external work, the structure of tractions and the micro tractions, and the local balance of actions and macro actions. If you remember what I said in the lessons of yesterday, in that case of continuum with the configuration of forces, it is not possible to to obtain all the balance equations only using the classical null invariance axioms. In this case, this is the expression of the work of the internal actions. Remember that S represents the macrostress tensor, and sans serif S represents the couple stress tensor, and zeta is the vector of the internal body actions, and the capital zeta is the microstress tensor. Using the divergence theorem, it is possible to derive through the virtual work principle. The internal work, a virtual internal work is equated to the virtual external work, and this is the expression of the work of the external actions, where B is a body force, WV is the standard displacement, capital B is the external body couple, and capital WV is the rotation, the micro-rotation, and this is an additional term of external body action, expanding work with the additional degree of freedom D, and this is on the bulk, on the body. On the surface of the body, we have, corresponding to all the kinematical field introduced, standard displacement, micro-rotation, and the additional displacement. These are the terms for the force on the boundary, F, the couple on the boundary, capital M, and the force on the microstructure that I named P. Okay, this is what I said before. Surface traction, surface couple, surface microtraction is the proper term. The structure of the tractions, that are the ones that I reported here, is then obtained as exactly a Cauchy theorem, using an expression that corresponds to the Cauchy theorem. So we have the standard stress. This is not really standard, but it's a stress. This is the normal to the boundary, and this is the force. This is a similar representation for the microstress tensor traction on the microstructure. And this is the same for the couple. By equating the internal work and the external work, also the local balance of actions and microactions can be obtained. And the first one is the macroforce balance. With on the boundary, the expressions with the boundary conditions that you can find on the right side of this slide. Note that the stress tensor is not standard because it's not symmetric. Then we have the microforces balance, that is the so-called configuration forces balance, and that is a non-standard equations that is added to the model and naturally derive only from the application of the divergence theorem and the application, of course, of the virtual work theorem in this generalized form. Then the equation of the moments in which appear the skew-symmetric part of the stress, because the stress is not symmetric. S is the so-called stress tensor, And S capital S, as I said before, is the coupled stress tensor. And these are the stress measure of a micropolar continuum with that is a continuum with the rigid microstructure. The other terms are less usual. We call these non-standard stresses, and in particular, zeta is, as I said also before, is an internal volume force. Remember the theory of degree 0 in the presentation of yesterday. And capital zeta is a configurational microstress. To have a naive idea of this additional force, I wish to show this picture in which you have a block, and this block rested on, for instance, on a spring of a stiffness K on the right side. This is not important. This is a naive interpretation for the additional force, zeta, that is a volume force, internal force, that is an important ingredient of the model. And if you consider the displacement of the point on the right side, you can, and this block, the weight of the block is represented by the vector of intensity P. You can evaluate the displacement using the stiffness K. But if the spring is damaged, in that case, you can evaluate a displacement that is greater, U star, that is greater from the original displacement, because the stiffness decreases. And this is the idea that underlines the models that are called the internal variables model. In the presentation of yesterday of damaged models by Professor Ibrahim Begovic, the continuum models to which he referred was internal variable models that describe the damage. And the damage is described in internal variable models as a reduction of the internal stiffness. In this model, the multifield model, instead, aiuto, sorry. Si blocca sulla diapositiva. Eccolo, ok. In this case, damage is represented as a state of additional or auto force. In Italian we say coazione. Coazione, sorry. In Italian questi li chiamiamo la teoria delle equazioni, se qualcuno conosce Colonnetti, ma insomma, is an additional force which wants to reproduce the decreasing of stiffness. And due to the fact that in the under rigid motion, not all the strain measures are null, it is necessary to require that the work of internal actions that in classical Cauchy, but also non-standard micromorphic model is null, because the strain measures under rigid motion are null. In that case, this case of configuration of forces, we have to add this equation. And we had to require that internal work under rigid motions, this star represents rigid motions, and here you can see the expression of the internal work in terms under rigid macro and micro motion. We derive an additional equation, an additional equation that acts as a constitutive prescription. That is a condition that must be required. And we can just say, following the approach of Antonio Di Carlo, that a constitutive prescription must be valid for any process. And for process, you can consider the response of a body under some, for instance, some actions. The response could be in terms of displacement, the strains and stresses. So a constitutive prescription, like an equation of this kind, must be valid for any process. While these standard balance equations that we obtained before by equating the internal and the external work must be satisfied by the solution of the continuum problem. So the process must be such that to satisfy the balance equation, because this is the solution of the problem, while the constitutive prescription must be valid for any process. The results in this case is quite interesting because it explains that the opening displacement D must have the direction of the traction on the microstructure. This will be more clear when we will discuss the example. This is also in essentially a micromoment additional balance equation. And this model, as I said before, it is easy to show, is intrinsically thermodynamically consistent. And the local dissipation inequality, that is the Clausius-Duhem generalized inequalities, allow us from an expression of the free energy to identify all the stress measures. I think that we have not much time to stop the lecture, but let me know if you are tired, bored, and if I can continue or do a break of 5 minutes. Marco. Huh? What do you say from the remote rooms? Could you send me a feedback? Nobody's there? Ci sono? Ci sono ancora, ragazzi? Hanno scritto in chat, però io la chat da qui non la vedo. Guardatela voi. Io da qui non posso uscire là. Vogliono? E va bene, allora facciamo 5 minuti di break. Riprendiamo? We will start. I partecipanti drastically reduced at 1:30. I'm afraid because the last part of the talk is applicative one and is easier to be understood. So with the aid of some numerical simulations for composite masonry materials, I want to focus on the advantages of non-local and in particular non-implicit, non-local micropolar modeling with respect, of course, to the classical continuum modeling. In the cases in which the internal length is comparable, as I said yesterday, to the structural macroscopic length. say that the structure of the multi-field continuum is encoded in its internal work formula that is reported in at the top of this slide. Remember that this is the stress tensor, and this is the strain measure of a standard micropolar continuum. That is the difference between the gradient of the standard displacement minus the micro-rotation, represented by a skew-symmetric tensor. This is another additional term related to the coupled stress that is represented by the tensor of third order sans serif S, and the gradient of the micro-rotation WV. This gradient of micro-rotation is also known as curvature tensor. Then this part is the additional part due to the configurational forces. The additional force zeta, that is a volume force interpreted as auto stress to the model, which describes the damage in this case, and the gradient and the macro stress tensor, capital zeta, which spends power with the gradient of the additional displacement D, which in a smeared sense represent the presence of the pores of the micrographs. So for the applications, 3 constrained cases I want to consider. And these cases are represented in this slide in the 3 columns. Let's start from the case in which only the microcracks or pores are present. In this case, we can think that there are no particle rotation, or the particle rotations are frozen to be equal to the local rigid rotation, as in the Voigt model, if you remember the lesson of yesterday. In that case, only the fluffs, the microcracks, has a role. And the continuum identified is the continuum with only the deformable affine microstructure. That means the porosity. And in this framework, as I said before, of course, representative volume element can be defined, and we consider as an application a material, polycrystalline ceramic matrix composite, in which the particles are rigid and the interfaces are deformable, but as the particles are not exactly rigid, their deformability is computed with the joint in terms of increasing of deformability of the joints. And at the interface, we use a joint equivalent stiffness, just to represent the deformability of the grains. And these are the variables that we used. This is a work that I performed with my colleague Anna Maria Pau some years ago. And what I want to show is just the reduction in stiffness due to damage, here say the porosity, represented by an additional state of stress and strain in the multi-field model. So damage is not represented as a decreasing of the stiffness, but as an autoforce additional state of stress and strain. And this is a case of a plate in tension, panel in tension, with the different level of porosity. And in this slide is show the variation in terms of number of pores, yes, in terms of pore density. In the left side, you can see the reduction in stiffness. This is on the vertical axis, the displacement at the middle of the panel, and on the horizontal axis, the pore size. On the horizontal axis, of course, we have the abscissa, the direction along the vertical direction. The reduction in stiffness can be represented by the multi-field model, as well by finite element models that accounts directly of the exact pore sizes and density. And this deduction in stiffness is comparable. And also the reduction in stiffness, this is represented when the size of the pores increases, and always has been also reproduced with the finite element model of the panel. And these results have been also compared by some other results in the literature, and we are still working at non-linear representation of this kind of material. But in the linear case, the correspondence has been found. These are the results of Sadowski's are mentioned in the slide for a similar case study. So the variation of porosity implies variation also on the displacement. Here in this slide you can see the total displacement versus the x-axis, that is the vertical axis. Due to the pore presence, so to the microstructure, we don't have, even in the elastic case, a linear displacement. So the ingredient of pore elements, that is represented by the additional the degree of freedom factor T, produces a non-linearity in the displacement. And my colleague Anna Maria Paul will explain how we decided to refine this model in order to better account of this quantity. This is a case of an elliptical cavity in a panel in tension. These are the constitutive equations of the model. You can recognize the stress measures that I introduced. And these constitutive equations, in the case in which we have no fibers or frozen fibers, so only the microcracks, depends on the gradient of the macro displacement U and on the gradient of the micro displacement D, that is the pores. This is the zeta, the additional configurational force, that depends in these formulations only on the displacement, additional displacement T, and this is the stress, micro stress capital zeta, which depends both on the macro displacement and on the gradient, of the macro displacement and on the gradient of the micro displacement. If these terms that due to the hyperelasticity of the model are equal, if this term is not null, the constitutive equations are coupled, because both variables appears in all the equations. This was defined as a coupling coefficient. Consider that in this equation the constitutive term O is equal to the constitutive term T due to the hyperelasticity, as I said before. And you can see, for instance, in this graph, which represents the variation of the total energy density at the crack tip, we can see that depending on the couple coefficient, this decay decreases. So this means that there is no more stress concentration at the crack tip. And one of the reasons of using this kind of continua is to reduce stress concentrations in the correspondence of some singularities, or geometrical, as in this case, or lowered singularities, as in the case that I will show in the following. This is another representation of the same phenomenon, and you can see that the energy distribution at the crack tip is decreases. This is a case, a general case, dynamic case of one-dimensional multi-field continuum, so a bar, and we can consider this a microcracked bar, in which these are the balance equations, the constitutive equations, in the case in which we have coupling. If, as I said before, we don't consider in the micro model interactions between particles and pores, slits, the equations, these are the Navier equations, become uncoupled. So the standard stress depends only on the micro displacement derivative. This is a one-dimensional model, and the additional micro stress depend only on the derivative of the micro model. This is an explicit solution, and we can see also that even in elastic case, the displacement due to the presence of porosity is not linear. And this has been represented, also validated, using a finite element formulation with the same level of porosity. And this is the nonlinearity of the actual response. Note that in the case of uncoupled balance equations, we have a coupling between the macro and the microstructure through the boundary conditions. I didn't enter into details of boundary conditions, but of course this allows that the two structures interact at the macroscopic level and the microscopic one. This is another result of a model, a bar in tension, represented with a finite element strip. We have, as described before, a reduction in stiffness due to the presence of the pores, pore density in this case, and this is the comparison between the explicit solution for the multi-field model with the additional displacement T and the finite element strip analyzed. This is instead the case of this is a dynamic case in which we considered free oscillations. And this is quite interesting concerning the feature that I presented before of a non-local model. And you can see here the macrowave equations and the microwave equations. And the term D is a coupling term. Note that the term in the microwave equation depending on the descriptor t, that is not the but not from its derivative, nor respect to the time, not respect to the time, nor respect to the space. So it's exactly the field T is the term which include the material internal length, and is the term that is responsible of the spatial dispersion in wave propagation. This is the identification of the constitutive terms, and in the case in which these particle-slit interactions are neglected, in this case the model is uncoupled, and the first equation is the standard macro wave equation, D'Alembert equation. The additional one is the equation with the dispersive term. If we consider wave propagation for this kind of problem that is decoupled, let's say decoupled when we don't consider the interaction between slits and particles in the lattice model. Anyway, this is a model of equations. This is a model in which the equations of macro and micro motions are decoupled. You can see that in the case of the micro wave equation, we have a dispersive equation due to the presence of this term d. And what does it mean? It means that in a standard wave equation, the velocity, the phase velocity depend on the ratio, on the square root of the ratio between the elasticity, the Young modulus, and the density of the medium. And the velocity is constant. In the case of a dispersive medium, we have a velocity which depends on the frequency or on the wave number, the length number, the wavelength, and so on. So the velocity is not constant. And so you can see in this graph. And focusing on the level of the damage inside the microstructure, consider the red line has the case in which there is high microcrack density per unit length. The green line is the case of medium microcrack density per unit length. And the blue one is the case of low microcrack density per unit length. And this is the dispersion diagram. On the vertical axis, you have the phase velocity, and on the horizontal axis, you have the wave number or the wavelength. You can see that in the presence of microcracks, the blue case is low density, the green is a medium, and the red is high. The velocity is not constant. This is the representation of the elastic, the velocity of the elastic bar. That is 2,000 meters per second. And what is interesting to observe is that in the case of high microcrack density, the wideness of the dispersion zone is higher, and it decreases by reducing the microcrack density. This means that after this critical wave number or critical wavelength, we have no more dispersion. So the extension of the dispersion area depends on the microcrack density. And this is 1 point. Moreover, we have a velocity. In this diagram, in the vertical axis is represented the phase velocity, and on the horizontal axis the microcrack density. So the velocity reduces when the microcrack's density increases. And on the right side of this picture, we have the amplitude of the waves. The amplitude of the waves increases if the microcrack density increases. And finally, due to this effect, we can find that waves propagate with distortion on the wave shape. And the kind of disturbance depends on the microcrack density, so on the level of damage. In the case, the blue one case, you can see this signal. In the case of medium microcrack density, this other, and this is the case in which the microcrack density is higher. The additional microdisplacement D then reveals the presence of the microcracks, the microstructure, as a disturbance spread along the bar that alters the shape and velocity of traveling waves. Just to enter into this phenomenon that is known in wave propagation as modulation, you can consider a case in which the red wave is the elastic one, the elastic wave, the macro wave. And the blue wave is a microwave. If you superpose these two waves, which propagates at a different velocity, you have this effect, that is a distortion. And distortion means that the waves, when propagate, encounter a crack and the shape is altered. And the velocity is, decreases. And from a phenomenological point of view, this is quite clear. And with the more details, we can define, this is the superposition of two waves, and we have here a long term, a carrier wave, and a long wave term, and a short wave term that can be defined by considering group velocity. Sorry for disappearing of the rating before, but this is the group velocity, and omega is the frequency. Omega WV is the frequency of the macrowave, and omega D is the frequency of the microwave. And KWV is the wave number of the macrowave, elastic, and the KD is the wave number of the microwave. So the difference between these two frequencies is delta omega, and the omega bar is the average velocity. So this difference is the group velocity, and this average is, of course, the average velocity. So in a dispersive phenomenon, the wave velocity, the group velocity, is always different from the average velocity. I am disoriented by animation in the PowerPoint, but this is the results that I want to show it to you. We have the group velocities defined as below, and the average velocity defined as below. And the superposition of these two waves, which propagates with different velocities, provide a distortion on the wave shape. And this distortion depends on the microcrack density. So in this slide, you can see the red one is the, let's say, the microwave. And the black one is the wave propagating in the damaged bar. So the total, the sum of the micro plus the micro wave. And in the case of low microcrack density, you can see that the peak-to-peak distance is higher. Then this reduces. This is in the right in this slide at the top, at the left side of the top. You can see something like a bit-like phenomenon. And this bit-like phenomenon corresponds to the encountering of crack during the wave propagation. This peak-to-peak distance reduces when the microcrack density increases, till the case in which all the wave, the resulting wave, is carried by the elastic one. The same occurs also in the case of coupled equations. These are the Navier equations for this problem, always in the case of free oscillations. And this term represents the level of the coupling. And the black one is the resulting wave, and the red one is still the elastic macro wave. And in the case of coupled constitutive equations, we can see that the wave shape of both resulting and macro waves changes, because there is an interaction between macro and the micro, and the amplitude of the total signal increases. This is the case. I don't want to enter into too much details, but it's worth noting that in the case of coupled equations, coupled constitutive equations, we have to solve an eigenvalue problem. And the dispersion relations for the wave velocities that are the eigenvalues of these equations, this is the so-called acoustic tensors, reveals the phenomenon of dispersion. And dispersion means that we have velocities depending on the frequency, or velocities depending on the wavelength or wave number. Note that it can be possible to demonstrate that this feature allows to the problem to be always well posed. In that case, the ellipticity of the static problem can be ensured, as well the hyperbolicity of the dynamic case. But what is important is to remember that an additional term of the multi-field mode problem is a regularizing term. So dispersion allows to take into account size effects in the models. This is another representation of similar concept. What is interesting is to find here that in the coupled constitutive case emerges two branches emerge from the solution of the dynamical problem of free oscillations, and the effects of coupling is such that to produce more dispersion effect when the coupling increases. Here is represented the dispersion diagrams in the uncoupled case and in the coupled case. In the coupled case, as I said before, you see that optical and acoustic branches arises. Acoustic means low frequency, and optical high frequency, high energy waves. By expressing everything in terms of influence of damage parameters of the microstructures, for instance, the size of the microcracks or the density of the microcracks, we can see that also in this case, the amplitude, the extension of the dispersive zone increases when the microcracks density or the microcracks length increases. So if the medium is more damaged, the dispersion effects are more relevant. Also in the case of forced oscillations, we have results which are represented in this slide. And you can see that from the case of low microcracks density to the case of high microcrack density, we have a variation not only on the velocity but also on the amplitude of the signal. And of course, if the bar is damaged, the amplitude is greater and the velocity is decreases. This is the way to consider the boundary conditions in that case. We have, as you see, Neumann boundary conditions, and I need more time to describe this, the way to take into account of these boundary conditions. I just want to show you the idea that is not very different from the idea of a Timoshenko beam. So in this case, a multi-field bar, we have the macroforce S and an additional microforce which represents the presence of the microcracks, the damage. By assigning the boundary conditions, we can consider that the microforce can depend on the macroforce. But when you study a Timoshenko beam, for instance, as in the picture in the slide, if you put the effect of a normal force that is not centered in the axis line, a Timoshenko beam, as I said also yesterday, is a one-dimensional model which preserves memory of the three dimensions of the body. So if you put a force not in the axis line, you have to put an additional force that in this case is a couple, the moment, that depends on the normal force, say the macroforce, N, and report this macroforce with a geometrical parameter that is the eccentricity to the axis line. So the microforce, in that case a moment, depends on the macroforce that is the normal force. So as in this case, there are some simulations that we performed and derived the expression for the coefficient which relates the microforce to the macroforces. don't want to enter into this detail because it's too late. And let me conclude with the case in which the material has not pores, no microcracks, but only the particles are present. In that case, only the rigid microstructure emerges. Remember that we have considered two kinds of microstructures, one named deformable and related to the presence of microcracks, and the other one named rigid. In this case, the microcontinuum model, the multi-field continuum model, is a Cosserat or micropolar model. These are the generalized Cauchy-Born rule in the case in which no voids are present. This is the expression of the internal density, the work, the density of the internal work, and the terms here reported are underlined as classical and non-classical. Mixed terms are removed just for considering material symmetry. And the non-classical term, in the case of micropolar model, as in the picture you can see, accounts for the relative rotation. Remember the difference between the local rigid rotation here called theta and the micro rotation that is the additional variable of the Cosserat model. And another term depends on the curvature, that is the gradient of the micro rotation, here represented by the skew-symmetric tensor WV. The stress conjugated terms for the relative rotation is the skew-symmetric part of the stress. And in the case of the curvature, the stress conjugated term is the couple stress. In this case, this is the same slide. Finally, if we consider both the constraints, so no particles, no rotation of particles, no voids, we get the classical model. To obtain the classical model, is sufficient to put the so-called void constraint. Remember that in the model of void, we have a control volume, a representative volume element that he called molecular sphere of action, in which all the particles have the same rotation. This means that the macro rotation equals the micro rotation. And correspondingly, we have also the vanishing of the couple stress. And then the Cauchy equivalent continuum is obtained with the classical internal density power formula. A quadratic expression of linearized displacement strain tensor named E. T is the Cauchy classical stress tensor. And this is a case in which we analyzed and compared the Cauchy and micropolar solution for a case of traction, shear, and 3-point bending test. This is a micropolar model compared to a classical Cauchy model. And we can observe in this picture that the Coursera solution on the left side of the picture, we have on the vertical line the energy that is normalized to the energy of the multi-field model that is normalized to the energy of a Cauchy anisotropic model. And on the horizontal axis, we have, as in the picture is shown, the orientation, the initial orientation of the fibers. And the solution of the Coursera in terms of energies here reported and compared to the solution of Cauchy model. Of course, also Cauchy accounts for the orientation of the fibers, but not as a Coursera model. And here, lambda corresponds to the choice of a given size for the elements. And the model is a model of bricks. A model of, is a matrix with the fibers oriented as represented in this slide. On the right side, we have selected the original orientation of the fibers, phi is p grec up to 4. So we choose an initial orientation for fibers, and the solution you can see, and this is quite interesting to observe. In the case of Coursera, on the vertical line, we also have the energy variation normalized to the Cauchy energy, the Cauchy anisotropic model, and the horizontal line, we have the size of the elements, of the fibers. And on this direction, toward the right side of the diagram, we have particles, fibers of smaller size. The solution of the Coursera model depends on the fiber size, while the solution of the Cauchy model does not. Even if the differences are more sensible if the fibers are initially rotated. But Cauchy has not scale parameters into the governing equations. And let me skip this slide. And here we represent the same model in the case of the 3-point bending test. On the left side, we can see the solution of the multi-field model. And in that case, the multi-field is a micropolar model. And on the right side, the solution of the Cauchy model. In particular, in this slide is represented the Coursera microrotation. That means corresponds, if you look at the original lattice model, to the orientations of the fibers. And in the Cauchy is the skew-symmetric part of the gradient of displacement that is called local rigid rotation. That is the rotation of a neighborhood of a point. So in the case of, these are the contour maps of the fiber rotation. And you can see that in the case of initial fiber rotation of 45 degrees, the effects are more evident. And this is the same results that in which the energy is represented, and you can look at this model as a model in the bottom case of flying cards, and this is the effect of deformations in correspondence of the application of the load. That, of course, the Coursera material, the Coursera model can represent. And darker colors indicate higher values of the fiber rotations. That is exactly in correspondence of the application of the load. I just want to spend some more words concerning the case in which we have a panel made of bricks of different size with a given texture, that means a given material class, and the solution represents the differences between micropolar and Cauchy while changing the load distribution. I don't want to enter into too much details because in the next lecture of Dr. Fantuzzi, some details will be analyzed, still analyzed. But here we can see that the solution depends on two scale factors. The scale factors are given by the size of the load print, here named A, and the size of the bricks. So we have two scale factors that affect the solution. And the solution in the micropolar case varies, of course, with the dimension of the bricks, small, medium, large. These are the constitutive equations. Let me skip and show also the results. The results here are represented in terms of vertical displacement, for instance, and you can see that in the case of more concentrated load, case 3, load case 3, we have more diffusion, and there is more diffusion in the case of large bricks. Cauchy solution, that is the solution at the on the left part of this slide, is not sensible to the variation of the size of the bricks. And the only case in which all the models give the same results is when the load is distributed. So this means that if we are in the presence of concentrated loads, we need a model with additional degrees of freedom, like a Coursera model. Moreover, we can observe that here on the horizontal axis is represented the line, the vertical line, the symmetry axis of the panel, and on the vertical axis is reported the displacement at the top. If we have a micropolar model, we have a reduced displacement because the micropolar model better distribute the load. And this can also be seen if we represent the vertical stress. These are the contour lines of the vertical stress, and in this case you can observe that for large bricks micropolar model distribute the load, and for large bricks the diffusion is higher. And this is also important to observe that in a similar case with the concentrated load, if we report on the vertical line the normalized strain energy, on the horizontal line the size of the elements, this is a kind of masonry, so the size of the bricks, we can observe that the Cosserat solution varies with the size, while the Cauchy, here the yellow line, does not vary with the size of the bricks. And in this diagram, the solution has been compared to the solution of a discrete model. And this discrete model is made of bricks and represent, in that case, the reality. So the Cosserat model exactly reproduce the discrete solution, the solution of the discrete system. And when the size vanishes, we don't obtain the solution of classical model of Cauchy. This is true only in the isotropic case, or at least a case of orthotropic material symmetry. So it is important, if you want to take into account the size, to consider a micropolar model. This is the same results that we obtained in a nonlinear case, and I just want to conclude my presentation and show that we was able to reproduce some experimental results. Here we have the collapse, we analyzed the collapse of big panels in our laboratory. And we observed that in the case of small bricks, with respect to the case of the bricks of a different length, we have collapse mechanism that is rotation of the particles. And the Cosserat model exactly represents the variation of these rotations. So the relative rotations of the real model is perfectly represented by the strain measure that is the curvature of the Cosserat micropolar model. This is also a comparison between Cauchy and Cosserat solution in a nonlinear constitutive case. And the reality also in this case is the solution of the discrete model. And the last slide that I want to show you, because I don't want to pass 2:30. By putting the same constraint that we put following Voigt for obtaining a classical continuum, if the deformation maps are not homogeneous, for instance, if these deformations are of the second order, we here have the second gradient of the standard displacement, and the continuum model derived is a second gradient continuum, also the model I presented yesterday. And the second gradient continuum has been used to be compared to Cosserat and to Cauchy. In the second gradient model, could you remember maybe that we have as additional strain measure the second the second order gradient of displacement, standard macro displacement, and a corresponding diffused, I call it this diffused hyperstress, microstress, that is work conjugated to the second gradient of displacement. So this is an analysis that I performed together with my colleague Anna Maria Pau, and it's interesting to show, considering brick assemblies, that the solution, of course, in the Courseratte and second gradient model depends on the size, besides on the shape of the bricks. So defining a scale ratio, that is the ratio, for instance, between the size of the bricks and the size of the panel, and an aspect ratio, that is the ratio between the height of the brick and the length of the brick, we can underline the effectiveness of the micropolar modeling. This is, for instance, a shear problem. This is the load case, a shear problem, this one. And these are the relative, the contour lines of the relative rotations. And remember that the relative rotations correspond to the skew symmetric part of the strain. So in this case, we have that the Courseratte solution always represents the solution of a discrete model in a quite perfect way, while the second gradient solution and the Cauchy solution do not. In particular, the second gradient model has the useful descriptors to represent the size of the elements, so has the internal length in the field equations, as of course the micropolar model, while Cauchy does not represent this feature because has not in the field equation any size parameter. But only the micropolar model has the possibility to represent an isotropy because the stress and the strain tensor is not symmetric. And the only case in which we have a correspondence of all the solutions is the orthotetragonal symmetry case. And the orthotetragonal symmetry case is the one represented in this slide, derived from a lattice model, a brick model made of square particles not interlocked. Only in this case we have the correspondence between the two solutions. And there is no time to enter into other details. Let me only to introduce the lecture of Dr. Tuna that will represent the first attempt, at least in my knowledge, to compare non-local, explicit or strong theories with implicit or weak theories. In that case, non-local explicit is the Haringen's model, and the non-local implicit theory corresponds to the micropolar model. We compare the results in various cases and focusing on the effects of the load singularity and in the Lott singularity, in which we can observe that both non-local models can distribute the load, and the Haringen model in a different, more convincing way. But Meral will enter into detail, so I can go quickly. And in the case of geometrical singularities, this is the case of a plate in tension with inclusion. And also in this case, we underline that non-local models are able to treat the problem of distribution of the load, and this is the results in the here are reported on the horizontal line. On the horizontal line is reported the value of the stress at the point in which the material where is the discontinuities, because we have a matrix and an inclusion of different characteristics, and you can see that both the Kosserath and the Haringen non-local model reduce the stress mismatch at the interface, and in the case of the Kosserath model, we also evaluate the stress intensity factor comparing to an explicit solution, and evaluate that in the micropolar modeling using a mesh refinement, a suitable mesh refinement, we obtain a very small error with respect to the explicit solution, differently from the Cauchy solution, but in this case also from the Haringen solution. And this is the last slide that I want to show you, just to remember that a non-local description for the composite complex materials can be given providing that a constitutive characterization of the model can be given. And in that case, we have all the features that we need to represent the microstructure and solve well-posed problems that are internal lengths, spatial dispersion, and thermodynamic compatibility. I think that we can stop and ask Dr. Maria Laura De Bellis to start at 3:30 because we are a bit late, so we have time to eat something and have a small rest. I don't know if you want to intervene in the discussion, but we can do this also in the afternoon. Mi faccio rivedere che stacchiamo la... No.